Hello and welcome to our journey through the invisible forces that govern our world. Tonight, we are not just talking about another theoretical physics scenario or astronomical phenomenon, but about the delicate balance that keeps everything we know from spinning into chaos. Literally, something extraordinary lies hidden in the very motion beneath our feet and around our planet. The relentless rotation that has shaped every moment of existence for over 4 billion years, spinning at over 1,000 miles per hour at the equator, while we remain blissfully unaware. This constant rotation, this cosmic dance that we call Earth's spin, is not merely background physics. Unlike the gentle forces we experience in daily life, this planetary motion is a messenger from the fundamental laws of the universe, its power shrouded in mysteries that become visible only when we dare to imagine what would happen if it stopped. What makes our planet's rotation even more astonishing isn't just its incredible speed and consistency, but the revelation that every living thing, every ocean, every breath of air exists in perfect harmony with this motion, a reality that we only truly appreciate when we consider what would happen if this cosmic clockwork suddenly ceased. Before we plunge deeper into this thought experiment, imagine where you are right now, sitting in a familiar world, perhaps unaware that you're actually hurtling through space at tremendous speed, that beneath your feet and all around you, the very fabric of physics is performing an intricate dance that keeps our world livable. If stories like this compel your imagination, consider subscribing or liking this program. It helps more curious minds connect and prepares us all to face the astonishing and sometimes unsettling truths that physics reveals about our existence. Now, take a moment. Let your mind reach back through the laws of motion and prepare to grasp what it truly means for a planet to suddenly stop, for the Earth itself to defy 4.5 billion years of physics, and what that single second would mean for everything we know. This is the beginning of a story where physics itself becomes both creator and destroyer, and we must confront the awesome power hidden in forces so constant we forget they exist until the moment they don't. At precisely noon on a Tuesday in March, somewhere above the Pacific Ocean, Earth performs an act that defies 4.5 billion years of physics. For exactly 1 second, our planet stops spinning. Not gradually, not with warning, but in an instant as complete as switching off a light. The sudden cessation creates a moment unlike any in the history of our world, a moment when the laws of motion become visible in ways no living thing was ever meant to witness. The planet beneath us halts, but everything else remembers the dance. Every molecule of air, every drop of water, every grain of sand maintains its eastward journey at the speed Earth had been carrying them. At the equator, this means traveling at 1,670 kilometers per hour. Near the poles, the velocity drops to nearly nothing. Between these extremes lies a gradient of catastrophic motion that reveals itself in the space of a heartbeat. Consider what happens in that first fraction of a second. A person standing in Quito, Ecuador, experiences the full force of equatorial motion. Their body, along with everything around them, continues eastward while the ground stops moving beneath their feet. Physics demands this continuation. Newton's first law becomes a brutal reality as the momentum stored in every object becomes a horizontal projectile motion problem on a planetary scale. Trees that have stood for centuries become missiles traveling at speeds that would make bullets seem leisurely. Buildings transform into launching pads for their own contents. The very air becomes a supersonic wind carrying everything not anchored to the suddenly motionless bedrock. The mathematics of this destruction follow precise patterns. At any given latitude, The rotational velocity equals Earth's circumference at that latitude divided by 24 hours. This creates a spectrum of devastation ranging from near calm at the poles to complete annihilation at the equator. Cities built along specific latitude lines face remarkably similar fates, despite being separated by vast distances. London and Calgary, both at roughly 51 degrees north, experience identical wind speeds of 1,050 kilometers per hour. Their buildings face the same physics, their populations the same impossible forces. The atmosphere itself becomes a player in this cosmic drama. Air masses that have circulated for millennia around our spinning world maintain their rotational velocity with the persistence of cosmic law. The troposphere, stratosphere, and mesosphere all continue their ancient eastward march, while the solid Earth beneath them stands perfectly still. This creates wind speeds that dwarf any hurricane ever recorded. Near the equator, the air moves at velocities approaching the speed of sound, creating a continuous sonic boom as it encounters any obstacle brave enough to remain standing. Scientists have long understood that Earth's atmosphere rotates with the planet due to friction and gravitational coupling. This coupling normally prevents the atmosphere from sliding across Earth's surface, but when the solid planet stops while atmospheric inertia continues, this coupling becomes the source of unimaginable turbulence. The boundary layer between moving air and stationary ground generates heat through friction at levels that transform local weather into something resembling controlled fusion reactions. Water responds with equal drama, but different timing. Ocean currents that have flowed in great loops around our rotating planet suddenly find themselves moving over a stationary seabed. The Coriolis effect, that subtle force that has guided oceanic circulation for millions of years, vanishes in an instant. The Gulf Stream, carrying 30 times the flow of all the world's rivers combined, becomes a temporary projectile following straight-line paths across ocean basins that no longer rotate beneath them. The immediate result creates tsunamis of unprecedented scale, not the focused waves generated by underwater earthquakes, but broad walls of water covering entire ocean basins. These liquid mountains race towards shorelines that have never experienced such forces. The Pacific Ocean's ring of fire becomes a ring of water as waves radiating from the suddenly altered circulation patterns converge on every coastline simultaneously. Coastal cities face waves that dwarf anything in recorded history, moving not just with gravitational energy, but with the accumulated momentum of entire ocean currents. The ocean's equatorial bulge, maintained for millions of years by centrifugal force, begins its collapse toward the poles as gravity reclaims water that rotation had pushed away from Earth's axis. This bulge represents a difference of 21 kilometers in Earth's diameter between equator and poles. As rotation stops, this excess water begins its journey poleward, creating a redistribution of mass that will eventually expose new continents at the equator, while drowning polar regions under unprecedented depths. Meanwhile, beneath our feet, the planet itself begins to respond. The Earth's crust, no longer held in its current shape by rotational forces, starts to adjust to new gravitational realities. Seismic waves radiate from every point where sudden stress changes occur. These are not ordinary earthquakes confined to fault lines, but global adjustments as the planet reshapes itself from a slightly flattened sphere back toward perfect roundness. The energy released in this global restructuring exceeds the combined force of every earthquake in recorded human history. Tectonic plates, locked in their current positions by millions of years of rotational stress, suddenly face new force distributions. The mid-Atlantic ridge experiences tension changes that propagate earthquake waves across both the Atlantic and Pacific basins. Subduction zones, where oceanic plates dive beneath continental ones, find their stress patterns completely altered. Volcanic systems that have remained dormant for centuries receive new pressure signatures that could trigger eruptions on every continent simultaneously. The most profound changes occur along lines of latitude. At the equator, the sudden absence of centrifugal force means everything becomes slightly heavier. Objects that weighed 100 kilograms now weigh 100.3 kilograms. This tiny change has enormous consequences when multiplied across the mass of entire continents. Mountain ranges experience new stresses as their constituent rocks become marginally heavier. Ocean basins deepen under the increased gravitational pull. The solid Earth itself begins a slow but inexorable migration toward its new equilibrium shape. Different latitudes experience these forces with varying intensity that follows mathematical precision. A person standing at Earth's North Pole would notice almost nothing in those first moments. The rotational speed there approaches zero, so the sudden stop creates minimal drama. Snow continues to fall vertically. Buildings remain intact. The aurora borealis continues its dance across magnetic field lines that remain, for now, unchanged. Even compasses continue to point north, though their relationship to geographic coordinates has fundamentally shifted. But travel southward, and the devastation intensifies with mathematical precision. At 30 degrees north latitude, the latitude of New Orleans, Cairo, or Tokyo, the rotational speed reaches 835 kilometers per hour. Cities at these latitudes experience partial devastation that follows predictable patterns. Structures oriented north-south experience maximum stress as debris flows become focused streams. East-west oriented buildings provide temporary shelter from the atmospheric hurricane, but face their own structural challenges as their foundations experience differential forces. At 45 degrees north, the latitude of Minneapolis, Milan, or Harbin, the rotational speed drops to 734 kilometers per hour. Still catastrophic, but survivable for those in the right locations with proper shelter. Underground facilities, subway systems, and basements carved into bedrock become havens where small populations might endure the initial atmospheric chaos. The biological world responds with equal variety, determined by latitude and local geography. Trees at different latitudes face different fates according to the wind speeds they encounter. Those near the poles bend slightly in the new wind patterns but remain rooted, their root systems adequate for the relatively mild forces they experience. Those at middle latitudes become part of a horizontal forest, toppled by winds no root system could withstand, but creating natural windbreaks that protect smaller organisms in their lee. Equatorial trees simply disappear, transformed into components of the supersonic atmospheric flow. Rainforests that have stood for millions of years become airborne in seconds, their biomass joining the great eastward migration of everything not anchored to bedrock. The Amazon, the Congo Basin, the forests of Southeast Asia all become temporary atmospheric phenomena rather than terrestrial ecosystems. Animals experience this moment according to their location and their ability to hold on to something solid. A bird in flight finds itself in an atmosphere moving faster than its wings can carry it, but also discovers that the air currents it depends on for navigation have been completely restructured. Ground-dwelling creatures become unwilling projectiles unless they happen to be sheltered behind substantial obstacles anchored to bedrock. Burrowing animals face the best survival odds, protected by Earth that moves with the planetary crust rather than the atmospheric flow. Marine life encounters a complete restructuring of their world. Deep ocean creatures, accustomed to the slow, predictable currents driven by Earth's rotation, suddenly find themselves in chaotic flow patterns as surface currents dive deep, and deep currents surface in patterns that have no precedent in marine biology. Fish migration patterns that have evolved over millions of years become instantly obsolete as the ocean currents that guide them transform beyond recognition. Human infrastructure reveals its vulnerability in seconds. Skyscrapers, designed to flex with wind and earthquake forces, face stresses no engineer ever calculated. Those aligned east-west experience maximum stress as their contents become horizontal projectiles launched from every window and opening. North-south aligned buildings become temporary barriers against the atmospheric flow, but their structural integrity depends entirely on whether their foundations can withstand forces applied horizontally rather than vertically. Transportation systems fail instantly across multiple domains. Aircraft in flight find themselves in atmospheric conditions no pilot trained for, with ground speeds and airspeed suddenly bearing no relationship to each other. Air traffic control systems lose all meaning as aircraft encounter wind conditions that exceed their design specifications. Ships at sea encounter waves that rewrite oceanography textbooks in real time, with rogue waves becoming the norm rather than the exception as ocean currents collide in patterns that have never existed before. Subway systems and underground transportation networks become either death traps or sanctuaries depending on their depth and orientation. Shallow tunnels experience differential forces as their eastern and western ends face different atmospheric pressures. Deep tunnels carved through bedrock provide some of the safest spaces on the planet, becoming inadvertent shelters for the few people lucky enough to be underground when the rotation stops. The technological systems that connect our modern world face immediate challenges that cascade through every network. Satellites in orbit continue their paths unchanged, but the ground stations they communicate with move eastward at up to 1,670 kilometers per hour before being destroyed by atmospheric forces. Global positioning systems provide coordinates for a planet that no longer rotates, making their calculations meaningless for any surface-based navigation. Communication networks designed around predictable signal paths must adapt to a world where the atmosphere moves at supersonic speeds, creating interference patterns that render most radio communications impossible. Cell phone towers become projectiles, internet cables snap under differential stresses, and the global communication infrastructure that connects modern civilization disintegrates within minutes. Power grids stretch and snap as transmission towers experience forces beyond their design limits. The continental power grids that distribute electricity across thousands of kilometers face a complete restructuring as towers topple in predictable patterns determined by latitude and local wind patterns. Nuclear power plants, built with multiple safety systems, face scenarios no safety protocol anticipated. The carefully maintained balance between electricity generation and consumption collapses as entire regions become uninhabitable within minutes, leaving power plants running without destinations for their output. Yet amid this global catastrophe, pockets of relative calm exist with mathematical predictability. Underground facilities near the poles experience minimal disruption. Deep caves and subway systems provide temporary shelter from the atmospheric chaos above. The people fortunate enough to be in these locations witness the transformation of their world through seismic vibrations and the distant rumble of a planet adjusting to new realities. These survivors become the inadvertent observers of Earth's most dramatic physical transformation. The sound of this moment defies description but follows predictable acoustic patterns. Near the equator, the air moves fast enough to create continuous sonic booms as debris breaks the sound barrier repeatedly. The collision between moving atmosphere and stationary obstacles generates a thunder that drowns out individual sounds of destruction. This acoustic environment exceeds pain thresholds and would cause immediate hearing damage to any observer not protected by substantial barriers. Further from the equator, the noise diminishes to a persistent roar proportional to local wind speeds, like standing next to a waterfall the size of a continent. At middle latitudes, the sound becomes a howling wind carrying the acoustic signatures of civilization being disassembled. Near the poles, relative quiet prevails, broken only by the distant rumble of seismic adjustments and the occasional crash of debris carried by more moderate winds. As the first second ends and the second begins, Earth starts to reveal the true scope of its transformation. The immediate projectile motion of the atmosphere and surface objects gives way to longer-term redistributions of mass and energy that will reshape the planet permanently. Ocean waters continue their journey toward the poles, carrying with them the dissolved minerals and nutrients that have maintained oceanic chemistry for millions of years. Atmospheric circulation patterns that have existed since the formation of Earth's current atmosphere begin reorganizing around new thermal gradients created by the absence of Coriolis forces. The trade winds, westerlies and polar easterlies that have driven weather patterns for geological ages become historical curiosities as new circulation patterns emerge based purely on thermal convection and pressure gradients. The magnetic field generated by our planet's rotating core faces its own crisis with implications that extend far beyond Earth's surface. The dynamo effect that has protected Earth from cosmic radiation for billions of years depends on the motion of conducting fluids in the outer core. With surface rotation stopped, the core's rotation relative to the surface changes dramatically. The magnetic field that has guided compasses and protected atmospheres begins a transformation that will reshape the relationship between Earth and space. In this moment of stillness, Earth reveals how intimately connected every aspect of our planet truly is. Rotation, which seems like such a simple concept, touches everything from the shape of ocean basins to the behavior of bacteria. The sudden absence of this fundamental motion creates a cascade of changes that will ripple through every system on our planet for millions of years to come. Yet even in this catastrophe, the planet demonstrates its resilience through the operation of physical laws that remain unchanged. The same forces that create such destruction also begin the process of establishing new equilibria. Water will find new paths to flow. Atmospheric circulation will reorganize around new patterns. Life will begin the long process of adaptation to a world where east and west have lost their rotational meaning, but north and south retain their magnetic significance. The moment of stillness lasts exactly 1 second, but its consequences will echo through the ages, reminding us that our spinning world is not just our home, but a complex, interconnected system where every motion, every force, and every rotation contributes to the delicate balance that makes life possible. In stopping for just 1 second, Earth teaches us that motion is not merely movement, but the foundation upon which our entire world is built. What happens when an ocean of air moving at 1600 kilometers per hour suddenly has no ground beneath it moving in the same direction? The atmosphere that surrounds our planet carries within its currents the memory of 4 billion years of rotation, each layer spinning in perfect harmony with the Earth below. When the solid world stops but the gaseous envelope continues its ancient journey eastward, we witness the birth of winds beyond anything in meteorological history. The atmosphere does not understand that Earth has stopped. Physics provides no mechanism for instant communication between the solid planet and the vast shell of gases that surrounds it. The troposphere, where weather lives and breathes, maintains its rotational velocity through pure inertia. The stratosphere above continues its own dance. Higher still, the mesosphere and thermosphere follow their separate patterns, each atmospheric layer suddenly moving at different speeds relative to the surface below. This creates a vertical wind shear, unprecedented in Earth's climatic history. Near the surface, friction attempts to slow the moving air, but the forces involved exceed anything the planet has ever experienced. The boundary layer, where air meets land, becomes a zone of continuous turbulence, generating heat through friction that transforms local temperatures in ways no climate model ever calculated. The heat generated by this friction approaches levels that create plasma formation in some regions, turning sections of the lower atmosphere into weakly ionized gas. Consider how this atmospheric memory expresses itself across different altitudes. At ground level, the air moves like a river flowing over a stationary riverbed, but unlike water, air compresses and expands, creating pressure waves that propagate through the atmosphere at the speed of sound. These pressure pulses collide and interfere with each other, generating acoustic patterns that turn the sky into a resonating chamber, playing notes no ear was designed to hear. The mathematics of this atmospheric behavior follow fluid dynamic principles, but at scales never before observed. The Reynolds number, which describes the ratio of inertial forces to viscous forces in fluid flow, reaches values that push atmospheric behavior into regimes previously only theoretical. Turbulent eddies form at sizes ranging from millimeters to hundreds of kilometers, creating a fractal pattern of atmospheric chaos that extends from ground level to the edge of space. The jet streams, those rivers of fast-moving air that circle the globe at high altitude, face their own crisis. These narrow bands of wind, traveling at speeds up to 400 kilometers per hour, even in normal conditions, suddenly find themselves flowing over a world that no longer rotates beneath them. The thermal gradients that maintain jet stream formation persist for now, but the Coriolis effect that guides their paths vanishes instantly. Without the Coriolis force, the jet streams begin to straighten from their familiar meandering patterns. Instead of flowing in great loops and waves around the planet, they start following more direct paths governed purely by pressure gradients and thermal differences. This straightening process redistributes the energy stored in these high-altitude winds, creating new patterns of convergence and divergence that generate vertical air movements on scales never before witnessed. The polar jet stream, normally confined to latitudes between 30 and 60 degrees, begins migrating toward new positions determined by temperature gradients alone. The subtropical jet stream, usually found between 20 and 30 degrees latitude, starts interacting with its polar counterpart in ways that create atmospheric interference patterns visible from space. Weather systems that depend on rotating air masses for their structure face immediate disintegration. Cyclones and anticyclones, those great wheels of air that have driven weather patterns for millions of years, lose the rotational force that maintains their circular motion. High-pressure systems, which normally rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, simply expand outward as their internal structure collapses. The Azores High, that persistent high-pressure system that normally dominates North Atlantic weather patterns, begins spreading eastward and westward simultaneously as its rotational structure dissolves. The Siberian High, a massive winter high-pressure system that brings cold air to much of Asia, loses its characteristic circulation and becomes a simple zone of dense cold air that spreads in all directions according to pressure gradients alone. Low-pressure systems undergo even more dramatic transformations. These areas of rising air normally maintain their structure through the balance between inward-flowing air and rotational motion. Without rotation, they become simple zones of vertical convection, creating towering columns of rising air that extend far higher into the atmosphere than any thunderstorm ever recorded. The Icelandic low, a semi-permanent low-pressure system that influences weather across the North Atlantic, transforms from a rotating system into a linear zone of rising air that extends across the entire width of the Atlantic basin. This creates precipitation patterns that bring rain and snow to regions that have never experienced such weather systems. The trade winds, those steady streams of air that have blown across tropical oceans for geological ages, continue their journey eastward while the oceans beneath them stop moving. This creates a unique situation where the wind patterns that have shaped maritime navigation and oceanic circulation for thousands of years suddenly become forces acting against stationary water surfaces. In the tropical regions, where trade winds normally blow at steady speeds of 20 to 30 kilometers per hour, the differential between moving air and stationary surface creates new forms of wave generation. Ocean surfaces, no longer rotating with their overlying atmosphere, experience wind stress patterns that generate waves traveling in directions that have no precedent in oceanographic records. The northeast trade winds of the northern hemisphere and the southeast trade winds of the southern hemisphere, which normally meet at the intertropical convergence zone to create a band of thunderstorms around Earth's equator, begin interacting in entirely new ways. Without Coriolis effects to maintain their characteristic angles, these wind systems start flowing more directly toward the equator, creating linear convergence zones that extend from coast to coast across entire ocean basins. The monsoon systems that bring seasonal rains to billions of people face complete disruption. These massive seasonal wind shifts depend on the differential heating of land and ocean combined with Coriolis effects to create their characteristic patterns. Without rotation, monsoons become purely thermal phenomena, creating new precipitation patterns based only on temperature differences between continental masses and adjacent waters. The Indian monsoon, which normally brings life-giving rains to over 1 billion people, transforms from a rotating seasonal system into a direct thermal circulation between the hot Indian subcontinent and the cooler Indian Ocean. This creates more intense but less predictable rainfall patterns that concentrate precipitation in narrow bands, rather than the broad seasonal patterns that have sustained agriculture for millennia. The African monsoon undergoes similar transformations, creating new patterns of rainfall that extend further north into the Sahara, while leaving traditional monsoon regions with altered precipitation, timing, and intensity. The complex interaction between Atlantic and Indian Ocean moisture sources, normally mediated by rotational effects, becomes a direct competition between thermal gradients. Hurricanes and typhoons, those great rotating storms that derive their power from warm ocean waters and sustained rotational motion, face extinction within hours. The eye of a hurricane, maintained by the balance between inward flowing air and centrifugal force, collapses as soon as rotational motion ceases. The organized spiral structure that concentrates a storm's energy into devastating winds dissolves into chaotic convection cells that spread the same energy across much larger areas. Yet the death of rotating storms does not mean the end of severe weather. The energy that once drove hurricanes still exists in the temperature differences between warm tropical waters and cooler air masses. This energy now expresses itself through different mechanisms, creating linear storm systems that stretch across continents, rather than circular storms that impact localized regions. These new storm systems, lacking rotational focus, spread their energy across broader areas but generate different types of severe weather. Instead of concentrated wind speeds reaching 200 kilometers per hour in small areas, These linear systems create sustained winds of 100 kilometers per hour across regions thousands of kilometers wide. Atmospheric pressure systems, which normally maintain their positions relative to Earth's rotation, begin new migrations across the surface. High pressure zones, no longer anchored by rotational dynamics, start flowing toward low pressure areas in direct paths rather than the curved trajectories imposed by Coriolis effects. This creates pressure gradients of unusual steepness, generating winds that follow mathematical curves rather than the complex patterns familiar to meteorologists. The pressure gradient force, normally balanced by Coriolis acceleration, to create the familiar circular wind patterns around pressure centers, now operates without opposition. This creates wind speeds directly proportional to pressure gradients, leading to more intense but shorter-lived wind events as pressure systems equalize more rapidly than ever before. The thermal circulation of the atmosphere undergoes fundamental restructuring. The three-cell circulation pattern in each hemisphere, Hadley, Ferrel, and polar cells, depends on the interaction between thermal gradients and rotational effects. Without rotation, these cells collapse into simpler convection patterns based purely on temperature differences between equator and poles. Near the equator, where solar heating remains most intense, air continues to rise and create areas of low pressure. But instead of dividing into distinct circulation cells, this rising air spreads both north and south in great sheets, creating linear weather patterns that extend from tropical regions toward both poles. The familiar zones of high and low pressure that create Earth's climatic regions begin redistributing into new configurations. The Hadley cell, normally extending from the equator to about 30 degrees latitude in each hemisphere, begins expanding poleward as rising equatorial air spreads directly toward the poles without being deflected by rotational forces. This creates a single convection cell in each hemisphere that extends from equator to pole, fundamentally altering global circulation patterns. The polar regions, normally characterized by cold, dense air masses that sink and spread outward, maintain their basic thermal characteristics, but lose the rotational component that normally deflects this spreading air into characteristic wind patterns. Cold air from both poles begins flowing directly toward the equator, creating head-on collisions with warm equatorial air masses that generate new forms of frontal weather systems. These colliding air masses create frontal boundaries that extend straight across continents rather than following the curved paths imposed by rotation. The result produces weather fronts of unprecedented length and intensity, bringing rapid temperature changes and severe weather to regions that normally experience more gradual climatic transitions. The polar front, normally a sinuous boundary between cold polar air and warmer mid-latitude air masses, straightens into linear zones of convergence that create weather patterns unlike anything in meteorological records. These straight fronts generate continuous lines of thunderstorms that extend from ocean to ocean across entire continents. Cloud formation patterns undergo their own transformation. The spiral cloud patterns visible in satellite imagery, created by the interaction of air currents with rotational forces, give way to linear cloud formations that stretch across entire hemispheres. Cumulus clouds, normally scattered randomly across landscapes by local convection and rotation-influenced wind patterns, begin organizing into vast linear arrays aligned with the new wind directions. Stratocumulus clouds, those low grey sheets that normally form through the interaction of stable air layers with surface heating, begin organizing into parallel bands that extend for thousands of kilometers. These cloud streets, as meteorologists might call them, create regular patterns of sunlight and shadow that march across continents with mathematical precision. The water cycle experiences profound modifications as atmospheric circulation patterns change. Evaporation from oceans continues based on temperature and humidity, but the transport of water vapor follows new paths determined by the altered wind patterns. Regions that have relied on rotationally driven weather systems for their rainfall face drought conditions, while other areas receive unprecedented precipitation from the new circulation patterns. The Amazon rainforest, normally sustained by moisture recycling through the interaction of local evaporation with rotating air masses, faces a complete restructuring of its water sources. The new linear wind patterns carry moisture in straight lines, rather than the complex loops that have maintained rainforest humidity for millions of years. Mountain ranges, which normally create predictable weather patterns through their interaction with rotating air masses, become generators of entirely new atmospheric phenomena. The orographic effects that create rain shadows and windward precipitation patterns operate under different principles when air flows follow direct paths rather than rotational curves. The Himalayas, normally creating complex precipitation patterns through their interaction with monsoon circulations, begin generating linear cloud formations that extend from the Bay of Bengal across the entire breadth of Asia. The orographic lift that creates precipitation on windward slopes now operates continuously along the entire mountain range rather than in seasonal patterns. The Rockies, Andes, and other major mountain chains begin creating standing wave patterns that extend far beyond their traditional areas of influence. Air masses forced upward by these barriers no longer follow curved paths around mountain systems, but create standing wave patterns that propagate across entire continents. Valley winds and mountain breezes. Those local circulation patterns created by differential heating of slopes and valleys persist but lose their rotational components. These local wind systems, normally deflected by Earth's rotation into predictable daily patterns, begin following more direct thermal gradients, creating new local climates in mountainous regions around the world. The atmospheric memory reveals itself most clearly in the upper atmosphere, where the thin air maintains rotational velocities for longer periods due to reduced friction. The aurora zones, normally confined to regions around Earth's magnetic poles, begin experiencing atmospheric conditions unlike anything in their history as high-altitude winds redistribute the charged particles that create these celestial light shows. Satellite imagery. For the brief period that communication systems remain functional, captures the transformation of global cloud patterns from familiar spiral and cellular structures to linear formations that stretch from horizon to horizon. The new atmospheric patterns create visual signatures that no meteorologist trained to read, transforming weather forecasting into an entirely new science. As hours pass after the initial stoppage, the atmosphere begins developing new equilibrium patterns. The thermal energy that drives weather systems continues operating, but now expresses itself through circulation patterns based purely on temperature gradients and pressure differences. The chaotic initial phase gives way to more organized flows, but these follow physical principles that create weather systems unlike anything in Earth's previous history. The atmosphere, with its long memory of rotation, slowly begins adapting to a world without spin. New circulation cells form based on thermal differences alone. Trade winds transform into direct thermal currents. Storm systems reorganize around vertical convection rather than rotational dynamics. The sky above our heads becomes unfamiliar territory where old rules no longer apply, and new patterns slowly emerge from atmospheric chaos. In this transformed world, the winds remember what Earth has forgotten. carrying in their currents the ghost of 4 billion years of rotation, while slowly learning to dance to new rhythms in a world that no longer spins. The atmosphere becomes both historian and prophet, preserving the memory of Earth's motion while writing the first chapter of a new climatic age. Across the vast expanse of the Pacific, a subtle change begins to ripple through waters that have circled the globe for millions of years. The ocean, that ancient dancer that has swayed to Earth's rhythm since the first rains fell, finds itself suddenly performing without music. The currents that have carried heat, nutrients and life across entire ocean basins continue their choreographed movements, but the stage beneath them has stopped moving. The ocean's response to Earth's sudden stillness reveals itself gradually, like a massive organism slowly awakening to a changed world. Unlike the immediate violence of atmospheric winds, water's greater density and thermal inertia create a more measured but ultimately more profound transformation. The seas hold within their depths the accumulated motion of 4 billion years of planetary rotation, and this stored energy must find new ways to express itself. Ocean currents represent some of the most powerful forces on Earth, moving volumes of water that dwarf all the rivers combined. The Gulf Stream alone transports more than 30 times the flow of all rivers on the planet, carrying 25 million cubic meters of water per second northward along the American coast. The Antarctic Circumpolar Current, the largest current system in the world, moves 150 times more water than all terrestrial rivers, circling the entire globe with a flow that connects all ocean basins. These massive flows of seawater suddenly find themselves traveling over an ocean floor that no longer moves beneath them. The immediate effect creates underwater weather systems unlike anything in oceanographic history. Deep ocean currents, normally guided by the subtle but persistent influence of Earth's rotation, begin following more direct paths determined purely by density differences and bathymetric features. The thermohaline circulation, that great conveyor belt of ocean water driven by temperature and salinity differences, loses the rotational component that has shaped its three-dimensional structure for geological ages. This circulation system, which regulates global climate by distributing heat from tropical regions to polar areas, begins operating under entirely new physical principles. Surface currents face even more dramatic changes. The trade wind-driven currents that circulate around the subtropical highs in each ocean basin lose their characteristic circular patterns as the Coriolis effect disappears. The North Atlantic Gaia, a clockwise circulation system that covers most of the North Atlantic, begins to unwind from its familiar spiral pattern. The South Pacific Gaia, the largest gyre system on Earth, starts dispersing its concentrated flow across broader areas. Consider the fate of the Gulf Stream, that river of warm water that carries tropical heat northward along the eastern coast of North America. This current, which moderates the climate of northwestern Europe by delivering Caribbean warmth to northern latitudes, suddenly finds itself flowing over a stationary ocean floor. The stream, normally focused into a ribbon of fast-moving water, 50 to 60 kilometers wide, begins to spread and diffuse as it loses the focusing effect of rotational forces. The Gulf Stream's characteristic meandering, those great loops and curves that oceanographers call rings and eddies, start straightening into more direct northward flow. This straightening process releases enormous amounts of kinetic energy that had been stored in the current's rotational motion, creating new forms of mixing between warm Gulf Stream water and the colder waters of the North Atlantic. The Kuroshio Current, which carries warm water northward along the coast of Japan, undergoes similar transformations. This current, known as the Black Stream for its deep blue color, begins to meander in new patterns as it adapts to the absence of Coriolis' guidance. The current's interaction with the colder waters of the Oyashio Current, normally confined to specific geographic boundaries by rotational effects, spreads across broader areas. The complex system of western boundary currents, powerful flows along the western edges of ocean basins, faces complete reorganization. The Brazil Current, the East Australian Current, the Agulhas Current off southern Africa, and similar systems all lose the rotational focusing that concentrates their flows into narrow, intense streams. These currents begin spreading across wider areas, reducing their velocity but affecting much larger geographic regions. Equatorial currents, those east-west flowing streams that have transported water across entire ocean basins for millions of years, face perhaps the most dramatic changes. The equatorial countercurrent, an eastward flowing current that normally runs against the trade winds due to rotational effects, loses its driving mechanism and begins to dissipate. This current, which has served as a major return flow for water transported westward by the trade winds, simply disappears within days of the rotational cessation. The north and south equatorial currents, normally deflected by rotation into complex patterns that create the characteristic east-west circulation of tropical oceans, start flowing more directly westward under the continued influence of trade winds. However, without the Coriolis effect to maintain their characteristic positions, these currents begin shifting latitudinally, creating new patterns of tropical circulation. The ocean's vertical structure experiences equally profound changes, upwelling and downwelling zones. Those areas where deep water rises to the surface or surface water sinks to the depths depend heavily on the interaction between wind patterns and rotational effects. The Ekman transport, a phenomenon where surface waters move perpendicular to wind direction due to Coriolis effects, disappears entirely, fundamentally altering coastal oceanography. The major upwelling systems along the western coasts of continents, which support some of the world's most productive fisheries, begin to reorganize as their driving mechanisms change. The Peru Current upwelling system, which brings cold, nutrient-rich water to the surface along the coast of Peru and northern Chile, transforms from a narrow band of intense upwelling into a broader area of vertical mixing. This system, which supports the world's largest single-species fishery in the form of anchovy populations, faces dramatic ecological consequences as the precise positioning of cold, nutrient-rich water shifts. The upwelling that has supported millions of seabirds, marine mammals and fish species begins operating under different principles, spreading nutrients across larger areas, but with reduced intensity. The California current system undergoes similar changes, with implications for marine ecosystems from Baja California to British Columbia. This system, which supports everything from tiny copepods to blue whales, begins distributing its nutrient-rich waters across larger areas, but with different timing and intensity patterns. Coastal upwelling systems around the world face restructuring as the winds that drive them change direction and intensity. The Benguela Current off the coast of southwestern Africa, which supports vast populations of sardines and other pelagic fish, begins operating under new physical principles. The Canary Current off northwestern Africa and similar eastern boundary current systems all face reorganization of their upwelling patterns. The thermohaline circulation, often called the ocean's conveyor belt, depends on the precise interplay between temperature differences, salinity gradients, and rotational effects. This circulation system, which moves water through all the world's oceans in a cycle that takes over 1,000 years to complete, begins adapting to new driving forces that operate on different timescales. The North Atlantic deep water formation, where cold, salty water sinks near Greenland and Iceland, to to begin its journey through the deep ocean basins, continues operating but with modified characteristics. The sinking water, no longer deflected by rotational forces into the characteristic spiraling patterns of deep water formation, begins following more direct paths toward the equator. This change affects the global distribution of dissolved oxygen, nutrients, and trace elements that deep water carries throughout the world's oceans. The deep water formation process, which normally creates distinct water masses with specific chemical signatures, begins producing different types of deep water with altered characteristics. Antarctic bottom water formation, where the coldest, densest water in the oceans forms around Antarctica and spreads northward along the ocean floor, also adapts to new conditions. This extremely cold water, with temperatures near -2 degrees Celsius, normally spreads through all ocean basins in characteristic patterns determined by seafloor topography and rotational effects. Without rotation, this bottom water begins following straighter paths as it flows northward from Antarctica, creating new patterns of deep ocean ventilation. The complex layering of water masses in the deep ocean, normally maintained by the subtle but persistent influence of rotation, begins reorganizing into simpler density stratified layers. The ocean's response to tidal forces undergoes fundamental changes as well. Tides, those rhythmic rises and falls of sea level driven by gravitational interactions with the moon and sun, lose their rotational component. The Coriolis effect normally deflects tidal flows into complex patterns that create the familiar tidal characteristics of different coastal regions. Amphidromic points, those locations in the ocean where tidal ranges approach zero due to rotational effects, disappear as the new tidal patterns establish themselves. The Bay of Fundy, famous for its extreme tidal ranges caused by resonance effects, amplified by rotation, begins experiencing different tidal patterns as the resonance frequencies change. Coastal regions that have experienced minimal tidal ranges for geological ages suddenly face significant tidal motions, while other areas see their extreme tidal ranges moderate as the flows redistribute. The Thames estuary, the Mediterranean Sea, and other bodies of water with unique tidal characteristics begin experiencing entirely new tidal regimes. The redistribution of ocean water begins slowly but follows inexorable gravitational principles. Earth's rotation normally creates an equatorial bulge in ocean surfaces, with sea levels roughly 21 kilometers higher at the equator than they would be if the planet were a perfect sphere. This bulge represents an enormous volume of water, trillions of cubic kilometers held in place by centrifugal force. As rotation ceases, this excess water begins its journey toward the poles, driven by gravity's attempt to restore equilibrium. The redistribution process creates the most profound long-term changes in ocean geography since the formation of the current ocean basins. This movement of water operates on timescales of decades to centuries, but its effects begin immediately as pressure gradients throughout the ocean system start changing. The excess water at the equator starts flowing poleward in currents, unlike anything in oceanographic history. These currents, driven purely by gravitational potential energy rather than wind stress or thermal differences, create new ocean highways that transport not just water, but also heat, salt, and marine life toward polar regions. The equatorial Pacific, the world's largest ocean basin, begins to empty its excess water at a rate that gradually exposes seabed areas that have been underwater since the formation of the modern ocean configuration. The East Pacific Rise, a massive underwater mountain range that normally lies 3,000 meters below sea level at the equator, begins approaching the surface as water levels drop. Simultaneously, Polar regions experience rising sea levels as the equatorial water arrives. The Arctic Ocean, normally constrained by ice and limited connections to other ocean basins through the Bering Strait and gaps between Greenland and Europe, begins expanding as unprecedented volumes of water arrive from equatorial regions. The Bering Strait, that narrow passage between Alaska and Siberia that normally restricts water exchange between the Arctic and Pacific, becomes inadequate to handle the massive flows of water moving poleward. The increased water volume begins finding new pathways, potentially opening new channels through the Canadian Arctic archipelago and around the northern edges of Greenland. Antarctic regions experience similar dramatic changes, though the presence of the massive Antarctic ice sheet complicates the process. The arriving water begins to undercut ice shelves and glaciers, creating feedback effects that accelerate ice melting and further change regional sea levels. The Ross Ice Shelf, the Filchner-Ronne Ice Shelf, and other massive floating ice formations face unprecedented water levels that affect their stability. Marine ecosystems face complete reorganization as their physical environment transforms. Ocean currents normally distribute heat, nutrients, and oxygen throughout the world's seas in patterns that have remained stable for millions of years. Marine life has evolved intricate relationships with these current systems, depending on them for migration routes, feeding grounds, and breeding areas. The great ocean migrations that have characterized marine life for geological ages begin to fail as the currents that guide them change course or disappear entirely. Grey whales, which migrate along the Pacific coast following specific current patterns and temperature gradients, find themselves in waters with altered characteristics that no longer provide the navigation cues their species has relied upon for millions of years. Sea turtles, which navigate across entire ocean basins using magnetic fields combined with current patterns, face double disruption as both their magnetic and oceanographic guidance systems change simultaneously. The loggerhead turtles that cross the Atlantic following the Gulf Stream find their traditional route altered as the current spreads and diffuses. The spawning grounds of many marine species depend on the precise intersection of currents, temperatures, and nutrient flows that create optimal conditions for reproduction. The Sargasso Sea, that unique ecosystem in the North Atlantic where American and European eels spawn, faces changes in its characteristic water conditions as the Gulf Stream's influence diminishes. Bluefin tuna, which cross entire ocean basins following specific current systems and temperature boundaries, encounter altered migration corridors that no longer provide the environmental cues their navigation systems require. These changes begin affecting their spawning cycles and feeding patterns within the first months after rotation stops. Coral reefs, those underwater rainforests that depend on specific temperature ranges and nutrient flows, face thermal stress as the currents that have moderated their temperatures for millions of years change course. The Great Barrier Reef faces altered patterns of water exchange with the open ocean as the East Australian current changes its characteristic flow patterns. Deep sea ecosystems, adapted to the slow but steady currents that bring nutrients and oxygen to the ocean depths, face their own challenges as circulation patterns change. The abyssal plains, those vast underwater deserts that depend on marine snow falling from surface waters and nutrients carried by deep currents, begin receiving different chemical inputs delivered by altered circulation systems. Hydrothermal vents, those underwater oases where unique ecosystems thrive around volcanic activity, experience changes in the deep water flows that bring them nutrients and remove their mineral-rich outputs. The tube worms, bacteria, and other specialized organisms that depend on these unique chemical environments face altered gradients that challenge their survival. The ocean's chemistry begins changing as different water masses mix in new patterns. The careful balance of nutrients, dissolved gases, and trace elements that has been maintained by stable circulation patterns starts shifting as waters from different regions encounter each other in unprecedented combinations. Ocean acidification patterns, normally distributed by predictable current systems, begin redistributing according to the new circulation patterns. Areas of the ocean that have maintained specific pH levels for thousands of years face chemical changes that affect everything from shell formation in marine organisms to the survival of microscopic plankton that form the base of marine food webs. The oxygen content of seawater, maintained by the circulation patterns that bring oxygen-rich surface water to the depths and return nutrient-rich deep water to the surface, faces redistribution as the conveyor belt circulation adapts to new driving forces. Oxygen minimum zones, those areas of the deep ocean with extremely low oxygen levels, begin shifting to new locations as circulation patterns change. As days and weeks pass, the ocean's response to its new environment becomes increasingly apparent. The immediate changes in current patterns give way to longer-term adaptations as water temperatures equilibrate across new pathways and marine ecosystems begin responding to their altered environment. The dance that began billions of years ago continues, but to a rhythm that no ocean has ever known. The sea, in its ancient wisdom, demonstrates both the fragility and resilience of Earth's systems. The same physical laws that create such dramatic disruption also begin establishing new patterns of circulation and distribution. Water continues to seek its level, currents reform according to available energy gradients, and marine life begins the slow process of adaptation to a world where ocean circulation follows entirely new principles. In this transformed seascape, the ocean remembers its past while discovering its future, carrying in its depths the memory of rotation while slowly learning the choreography of a world that no longer spins. The last dance of the rotating Earth gives way to the first movement of a new oceanic age, where currents flow to different rhythms and marine life must adapt to patterns that have no precedent in Earth's long history. Earth's magnetic field extends 60,000 kilometers into space, creating an invisible shield that has protected our planet from cosmic radiation for over 3 billion years. This magnetic envelope, generated by the churning motion of liquid iron in Earth's outer core, depends fundamentally on the planet's rotation to maintain its strength and configuration. When that rotation stops, even for a single second, the dynamo that creates our magnetic protection begins a transformation that will reshape the relationship between Earth and the cosmos. The magnetic field we observe at Earth's surface represents just the visible portion of a vast, complex system that extends far beyond our atmosphere. The magnetosphere, that teardrop-shaped bubble of magnetic influence surrounding our planet, stretches from the surface to distances greater than the orbit of the Moon. This invisible barrier deflects charged particles streaming from the Sun, channels cosmic radiation away from populated areas, and creates the spectacular aurora displays that dance across polar skies. Scientists have long understood that Earth's magnetic field originates in the outer core, a layer of liquid iron and nickel located between 3,000 and 5,000 kilometers below the surface. This metallic ocean, heated by radioactive decay and primordial heat from Earth's formation, circulates in complex patterns driven by thermal convection and the planet's rotation. The interaction between these flowing conducting liquids and Earth's rotation creates the dynamo effect that generates our magnetic field. The dynamo mechanism operates on principles similar to those found in electrical generators, but on a planetary scale. As electrically conducting fluids, move through existing magnetic fields, they generate electric currents, which in turn create new magnetic fields. The rotation of the planet organizes these flows into the large-scale patterns necessary to maintain a stable dipolar magnetic field with north and south poles. When Earth's rotation suddenly ceases, this carefully balanced system faces immediate disruption. The outer core, with its enormous thermal inertia, continues its rotational motion even as the solid planet stops. This creates a differential rotation between the solid Earth and its liquid core, fundamentally altering the dynamo processes that have maintained our magnetic field for billions of years. The change does not happen instantly. Magnetic fields, especially those generated by planetary scale processes, respond to changes over periods ranging from years to millennia. However, the disruption of the core's rotational patterns begins immediately, setting in motion changes that will gradually weaken and reorganize Earth's magnetic protection over the coming decades and centuries. The geomagnetic field strength, currently averaging about 50 microtesla at Earth's surface, begins a slow but measurable decline as the core dynamo adjusts to new conditions. This weakening does not occur uniformly across the planet's surface. Some regions experience faster magnetic field decay, while others maintain stronger fields for longer periods, creating a patchy pattern of magnetic protection that has no precedent in Earth's history. The magnetic poles, those points where Earth's magnetic field lines converge, start wandering from their current positions as the field configuration changes. The magnetic North Pole, currently located in the Canadian Arctic and already moving at speeds of several dozen kilometers per year, begins accelerating its migration as the field reorganization accelerates. The magnetic South Pole, located off the coast of Antarctica, undergoes similar displacement. This pole migration affects navigation systems worldwide. Magnetic compasses, which have guided travelers for over 1,000 years, begin pointing toward moving targets. The magnetic declination, the difference between magnetic north and true north at any given location, starts changing at rates that make existing navigational charts obsolete within months, rather than the decades normally required for updates. Aviation systems face immediate challenges as magnetic compass readings become increasingly unreliable. Aircraft navigation, which still depends on magnetic headings for many procedures, must adapt to a world where magnetic north moves at unprecedented rates. Airport runways, numbered according to their magnetic headings, face renaming as their magnetic orientations shift beyond acceptable tolerances. Marine navigation experiences similar disruptions. Ships at sea, particularly those operating in remote areas where GPS signals may be unreliable, depend on magnetic compasses for backup navigation. The rapid changes in magnetic declination create navigation errors that accumulate over long voyages, potentially causing significant position uncertainties. The biological world faces perhaps the most profound consequences of magnetic field changes. Millions of species have evolved sophisticated magnetic sensing abilities that guide their navigation across vast distances. These biological compasses, refined over millions of years of evolution, suddenly begin receiving signals that no longer correspond to familiar geographic locations. Migratory birds, which navigate using a combination of magnetic fields, stellar positions, and geographic landmarks, encounter unprecedented challenges as their magnetic guidance systems provide conflicting information. Arctic terns, which migrate from Arctic to Antarctic regions in the longest migration of any animal, find their magnetic navigation cues shifting in ways that could lead them far from their traditional routes. The magnetic sensing abilities of birds depend on specialized cells containing magnetite crystals and possibly quantum mechanical processes in certain proteins. These biological compasses, sensitive to both magnetic field strength and direction, begin receiving altered signals as Earth's magnetic field configuration changes. The result disrupts migration patterns that have remained stable for millions of years. Sea turtles face equally dramatic challenges. These ancient mariners navigate across entire ocean basins using magnetic field signatures that correspond to specific geographic locations. Each region of the ocean has a unique magnetic signature based on field strength and inclination angle. As these signatures change, turtles lose the ability to navigate to traditional nesting beaches and feeding grounds. The loggerhead turtles that hatch on beaches along the southeastern United States normally follow magnetic guidance to enter the Gulf Stream system, where they spend their early years feeding in floating sargassum mats. The changing magnetic signatures could misdirect these young turtles away from the currents that support their survival, potentially causing massive population impacts. Marine mammals also depend on magnetic navigation for their long-distance movements. Whales, which undertake some of the longest migrations in the animal kingdom, use magnetic field information combined with other navigational cues to traverse entire ocean basins. The humpback whales that migrate between Alaska and Hawaii, covering distances of up to 25,000 kilometers annually, could find their traditional routes disrupted by changing magnetic conditions. The impact extends to smaller creatures as well. Salmon returning to their natal streams use magnetic field information as part of their navigation system. The Pacific salmon that swim thousands of kilometers through the open ocean to return to the specific streams where they were born could lose this crucial navigational aid, potentially disrupting entire ecosystems that depend on salmon runs. Even bacteria are affected by magnetic field changes. Magnetactic bacteria, microscopic organisms that contain chains of magnetite crystals, use Earth's magnetic field to orient themselves in aquatic environments. These bacteria play important roles in biogeochemical cycles, helping to process nutrients and maintain water quality in marine and freshwater systems. The magnetosphere, that vast region of space dominated by Earth's magnetic field, begins reshaping as the field's strength and configuration change. This invisible barrier normally deflects most of the charged particles streaming from the Sun, protecting Earth's atmosphere and surface from harmful cosmic radiation. As the magnetic field weakens, the magnetosphere contracts, allowing more cosmic radiation to penetrate closer to Earth's surface. The Van Allen radiation belts, those toroidal zones of energetic particles trapped by Earth's magnetic field, begin changing their size and position as the trapping efficiency of the magnetic field decreases. Satellite operations face increasing challenges as the radiation environment in near-Earth space becomes more hazardous. Communications satellites, GPS systems, and Earth observation platforms all depend on the magnetosphere's protection to shield their sensitive electronics from cosmic radiation. As this protection weakens, satellite lifespans decrease and failure rates increase. The International Space Station and other crewed space missions encounter elevated radiation levels that require changes in operational procedures. Astronauts face increased exposure to cosmic radiation, particularly during solar storms when the Sun emits additional charged particles. Mission planners must develop new protocols for protecting crew members in the altered radiation environment. Ground-based technology systems also face impacts from the changing magnetic field. The aurora zones, normally confined to high latitudes where magnetic field lines channel charged particles into the atmosphere, begin expanding toward lower latitudes as the field configuration changes. This expansion brings auroral activity and associated electromagnetic interference to regions that have never experienced such phenomena. Power grids, in areas newly exposed to auroral activity, face disruptions from induced electrical currents. These geomagnetically induced currents can damage transformers and cause widespread power outages in regions not equipped to handle such effects. The electrical infrastructure of temperate zones, designed without consideration for geomagnetic effects, proves vulnerable to these new electromagnetic environments. Radio communications experience increased interference as the ionosphere, that electrically charged layer of the upper atmosphere, responds to changing patterns of cosmic radiation. The ionosphere, maintained by solar radiation and cosmic ray interactions with atmospheric gases, begins developing new characteristics as more cosmic radiation penetrates the weakened magnetosphere. High-frequency radio communications, which depend on ionospheric reflection to achieve long-distance propagation, face unpredictable signal conditions. Amateur radio operators, military communication systems, and emergency services that rely on HF radio find their communication links becoming increasingly unreliable. The aurora themselves, those magnificent displays of light that have inspired human cultures for thousands of years, begin appearing in new locations as the magnetic field configuration changes. The northern lights, traditionally visible only in Arctic and subarctic regions, start appearing at lower latitudes as magnetic field lines reorganize. These auroral displays, while beautiful, indicate the increased penetration of charged particles into Earth's atmosphere. The same particles that create the colorful light shows also contribute to atmospheric heating and chemical changes that can affect climate patterns and atmospheric composition. Climate systems begin responding to the increased cosmic radiation as high-energy particles interact with atmospheric molecules to create new chemical species. Cosmic rays normally create small amounts of radioactive carbon-14 and other isotopes in the upper atmosphere. With increased cosmic ray penetration, the production of these isotopes increases, potentially affecting global carbon cycles. The ozone layer, which protects Earth's surface from harmful ultraviolet radiation, faces additional stress from cosmic ray interactions. High-energy particles can break apart ozone molecules and create nitrogen oxides that further deplete ozone concentrations. This depletion occurs in addition to any effects from changing atmospheric circulation patterns. Agricultural systems must adapt to increased cosmic radiation levels reaching Earth's surface. While the immediate increase may be small, sensitive crops and livestock could experience subtle effects from elevated radiation exposure. The long-term cumulative effects of increased cosmic radiation could influence plant genetics and ecosystem dynamics in ways that are difficult to predict. Human health considerations become increasingly important as the magnetic shield weakens. While Earth's atmosphere provides significant protection from cosmic radiation, the increased particle flux could contribute to higher cancer rates and genetic mutations over time. Populations living at high altitudes, where atmospheric protection is reduced, face the greatest increases in radiation exposure. Archaeological evidence suggests that ancient human civilizations may have been affected by previous magnetic field changes. Cave paintings and stone monuments aligned with magnetic north from thousands of years ago no longer point in the directions their builders intended, indicating that significant magnetic changes occurred even during recorded human history. The current situation, however, unfolds at rates that dwarf any previous magnetic field changes documented in human records. Research institutions begin international collaborations to monitor and understand the changing magnetic field. The International Association of Geomagnetism and Aeronomy Coordinates global efforts to track field changes and develop new models for predicting magnetic field behavior under non-rotating conditions. Scientists realize they are witnessing a natural experiment that provides unique insights into planetary magnetic field dynamics. The changing magnetic field creates opportunities for new scientific discoveries about Earth's internal processes. The rapid rate of change allows researchers to observe dynamo processes that normally operate on geological timescales, providing real-time data about core dynamics that could revolutionize understanding of planetary magnetic field generation. Wildlife rehabilitation centers begin receiving increased numbers of disoriented migratory animals as magnetic navigation systems fail. Sea turtle rescue operations report growing numbers of animals stranded far from their normal ranges, while bird migration monitoring stations document unusual flight patterns and timing changes in species that have maintained consistent migration schedules for thousands of years. The economic impacts of magnetic field changes begin affecting industries dependent on magnetic navigation. Shipping companies must invest in upgraded navigation systems less dependent on magnetic compasses, while aviation authorities develop new procedures for aircraft navigation in the changing magnetic environment. The costs of these adaptations create economic pressures throughout transportation industries. Military applications face particular challenges as many navigation and targeting systems incorporate magnetic field measurements. Naval vessels using magnetic compasses for backup navigation must develop new procedures for operating in the changing magnetic environment. Military bases located at high latitudes begin experiencing auroral interference with communications and radar systems. As the magnetic field continues its transformation, Earth embarks on a new chapter in its magnetic history, creating conditions that have no precedent in the geological record and challenging life on Earth to adapt to a world where the magnetic compass no longer points toward familiar directions. The invisible shield that has protected our planet for billions of years must find new configurations, while the life it has sheltered learns to navigate without the guidance of the poles that have anchored direction throughout Earth's history. From the smallest bacterium, measuring mere micrometers, to the largest blue whale stretching 30 meters through ocean depths, every living organism on Earth operates according to internal clocks, calibrated to our planet's 24-hour cycle. These biological timepieces, refined through billions of years of evolution, suddenly find themselves keeping time for a world that no longer follows the rhythm they were designed to match. When Earth stops rotating and creates days and nights lasting 6 months each, life faces a temporal crisis that touches every cell, every heartbeat, and every breath. The circadian clock, that masterpiece of biological engineering, operates within nearly every living cell on our planet. This internal timekeeper, more precise than many human-made chronometers, coordinates everything from sleep cycles in mammals to photosynthesis in plants to reproductive timing in microorganisms. The word circadian itself means approximately a day, reflecting the fact that these biological rhythms evolved to match Earth's rotation period with remarkable accuracy. In humans, the circadian system involves a complex network of molecular mechanisms that operate like interlocking gears in a cosmic watch. The suprachiasmatic nucleus, a cluster of approximately 20,000 neurons located in the brain's hypothalamus, serves as the master clock that coordinates biological timing throughout the body. This neural timekeeper receives information about light and darkness through direct connections to the eyes, allowing it to synchronize internal rhythms with the external environment. When the external environment suddenly changes from 24-hour cycles to 6-month periods of continuous light and darkness, This synchronization system faces unprecedented challenges. The molecular machinery that has evolved to respond to daily light cycles cannot simply readjust to periods nearly 200 times longer than those for which it was designed. At the cellular level, circadian rhythms depend on feedback loops involving specific genes and proteins that oscillate in predictable patterns. The clock and BMAL1 proteins bind together to activate genes that produce other proteins, including PIR-E and CRY, which eventually inhibit their own production. This creates a molecular oscillation that takes approximately 24 hours to complete one cycle under normal conditions. These protein oscillations control the timing of numerous physiological processes. Body temperature fluctuates in predictable patterns, typically reaching its lowest point in early morning and its highest in late afternoon. Hormone production follows similar schedules, with cortisol levels peaking in the morning to prepare the body for daily activities and melatonin rising in the evening to promote sleep. The disruption of these rhythms creates immediate health consequences for humans and other mammals. Sleep-wake cycles, normally regulated by the interaction between light exposure and melatonin production, lose their environmental cues. In regions experiencing continuous daylight, melatonin production becomes suppressed indefinitely, leading to chronic insomnia and the health problems associated with persistent sleep deprivation. Conversely, areas plunged into 6 months of darkness experience continuous melatonin production, creating a state resembling permanent sleepiness. The human body evolved to experience roughly 8 hours of darkness per day, faces physiological stress when exposed to months of continuous dark conditions. The metabolic consequences prove equally severe. Human metabolism follows predictable daily patterns, with insulin sensitivity typically highest in the morning and declining throughout the day. Digestive enzymes are produced according to anticipated meal times, while liver function cycles through different phases of nutrient processing and detoxification. Without regular day-night cycles to provide timing cues, these metabolic rhythms begin to drift out of synchronization with each other and with behavior patterns. Blood sugar regulation becomes increasingly difficult as insulin production loses its temporal coordination. Liver function becomes erratic, affecting the body's ability to process nutrients and eliminate toxins effectively. Cardiovascular systems experience similar disruption. Heart rate and blood pressure normally follow circadian patterns, with blood pressure typically lowest during sleep and highest during active periods. The cardiovascular system's circadian regulation helps coordinate blood flow with anticipated activity levels and metabolic demands. The immune system, which relies heavily on circadian timing to coordinate its various functions, faces particular challenges. Many immune responses are timed to coincide with periods when infection risk is highest, while tissue repair and regeneration are scheduled for rest periods when energy can be devoted to maintenance rather than activity. Plant life faces equally dramatic challenges as photosynthesis systems evolved for daily light cycles, encounter months of continuous illumination or darkness. In regions of perpetual daylight, plants initially attempt to maintain their normal photosynthetic rhythms, but the absence of dark periods prevents the completion of essential biochemical cycles that require darkness to function properly. Photosynthesis involves two major sets of reactions: the light-dependent reactions that capture solar energy, and the light-independent reactions that use this energy to synthesize organic compounds from carbon dioxide. While continuous light might seem advantageous for energy capture, many plants require periods of darkness to complete essential metabolic processes and prevent the accumulation of toxic byproducts from continuous photosynthesis. Trees and other long-lived plants face particular stress as their seasonal timing systems lose synchronization with environmental conditions. Many temperate plants use day length as a primary cue for timing events such as leaf production, flowering, and preparation for dormancy. With day length suddenly extending to 6 months, these timing systems provide conflicting signals that can trigger inappropriate responses. Fruit trees might attempt to flower continuously during the 6-month day period, exhausting their energy reserves and failing to produce viable fruit. Deciduous trees might fail to enter dormancy properly, leaving them vulnerable to temperature fluctuations and unable to survive the altered seasonal patterns. Agricultural systems face collapse as crop plants lose the environmental cues they depend on for growth and reproduction. Grain crops such as wheat, rice, and corn require specific photoperiod cues to trigger flowering and seed production. Rice, for example, is typically a short-day plant that flowers when day length falls below a critical threshold. With day lengths of 6 months, rice plants might never receive the signal to begin reproductive development. Vegetable crops face similar challenges. Tomatoes, peppers, and other fruiting plants depend on regular day-night cycles to coordinate flower production with fruit development. Continuous light can cause excessive vegetative growth at the expense of fruit production, while continuous darkness prevents photosynthesis entirely. Pollination systems collapse as the timing relationship between flowering plants and their pollinators becomes disrupted. Many flowering plants have evolved to bloom at specific times of day when their preferred pollinators are most active. Bees, for example, typically forage during daylight hours and return to their hives at night to process nectar and communicate location information to other workers. With 6-month day periods, bees face the physiological stress of continuous activity without the restorative dark periods they require for hive maintenance and development. Bee colonies might exhaust themselves during the continuous daylight period, while the lack of fresh flowers during the 6-month night period could lead to starvation. Aquatic ecosystems experience their own circadian disruptions. Many marine and freshwater organisms follow daily vertical migration patterns, moving between different depths according to light conditions. Zooplankton typically rise toward the surface at night to feed on phytoplankton while avoiding visual predators, then descend to deeper waters during daylight hours. These daily vertical migrations, sometimes called the greatest migration on Earth due to the enormous biomass involved, transport nutrients between different ocean layers and play crucial roles in marine food webs. The disruption of these migration patterns affects the entire oceanic food chain, from the smallest plankton to the largest whales that depend on predictable concentrations of prey organisms. Fish species that rely on daily feeding patterns face starvation or overconsumption depending on their location. Many fish are adapted to feed during specific periods of the day when their preferred prey organisms are most abundant and vulnerable. Some species feed primarily at dawn and dusk, taking advantage of the transition periods when prey animals are most active. Marine mammals face particular challenges as their behavior patterns evolved around predictable day-night cycles. Dolphins and whales often follow daily activity patterns that include specific periods for feeding, socializing, and resting. Some species engage in coordinated hunting activities that depend on precise timing between group members. The disruption of these behavioral patterns affects not only the marine mammals themselves, but also their prey species, which have evolved anti-predator behaviors timed to coincide with periods of high predation risk. The collapse of these predator-prey timing relationships cascades through marine ecosystems in ways that are difficult to predict. Coral reefs, those underwater cities that support enormous biodiversity, depend on daily rhythms for many essential processes. Corals themselves exhibit circadian patterns in their symbiotic relationship with zooxanthellae, the microscopic algae that live within coral tissues and provide them with nutrients through photosynthesis. Many coral species engage in synchronized spawning events timed to specific moon phases and daily periods when conditions are optimal for reproductive success. The disruption of circadian rhythms could prevent these spawning events, threatening the reproduction of entire coral communities and the countless species that depend on healthy reef ecosystems. Nocturnal animals face particularly severe challenges as their evolutionary adaptations for nighttime activity become either permanently advantageous or completely useless depending on their geographic location. Bats, which have evolved sophisticated echolocation systems for navigating and hunting in darkness, might find themselves with either 6 months of optimal hunting conditions or 6 months of intense competition with diurnal species suddenly active in continuous daylight. Owls and other nocturnal predators, adapted for hunting in low light conditions, might struggle with continuous daylight, while their prey species face the reverse challenge of avoiding predators that can now hunt continuously for 6 months rather than only during nighttime hours. The migration patterns that connect ecosystems across vast distances face complete disruption. Many species time their migrations to coincide with seasonal changes in day length, using photoperiod as a reliable cue for when to begin long-distance movements between breeding and feeding areas. Arctic terns, which undertake the longest migration of any animal by traveling from Arctic to Antarctic regions annually, depend on predictable seasonal changes in daylight hours to time their movements. With day length suddenly becoming 6 months in each hemisphere, these birds lose the environmental cues that have guided their species for millions of years. Monarch butterflies, which migrate thousands of kilometers between breeding areas in North America and overwintering sites in Mexico, use day-length changes as triggers for different phases of their migration. The disruption of photoperiod cues could prevent entire populations from completing their life cycles successfully. Seed dispersal mechanisms that depend on animal behavior patterns face disruption as the timing relationships between plants and their dispersal agents change. Many fruit trees time their fruiting to coincide with peak activity periods of birds and mammals that consume their fruits and disperse seeds to new locations. The breakdown of these timing relationships affects forest regeneration and plant community dynamics across all ecosystems. Without effective seed dispersal, plant populations become isolated and face increased risk of local extinction, while new areas suitable for colonization remain unreached. Human societies must adapt to the psychological and social consequences of altered day-night cycles. Cultural practices, work schedules, and social rhythms evolved around predictable daily cycles that suddenly no longer exist. The psychological effects of continuous daylight or darkness create challenges that extend far beyond individual health impacts. Sleep disorders affect entire populations simultaneously, creating unprecedented public health challenges. Healthcare systems must develop new approaches for managing the widespread circadian rhythm disorders that affect every person on the planet. The social and economic costs of population-wide sleep disruption strain societies already dealing with the physical consequences of Earth's rotational changes. Educational systems face the challenge of maintaining normal learning schedules when natural day-night cycles no longer provide timing cues. Children whose developing circadian systems are particularly sensitive to environmental changes require special attention to maintain healthy sleep patterns and cognitive development. Research facilities studying circadian biology find themselves observing the breakdown of biological timing systems in real time. Sleep laboratories record dramatic changes in human sleep architecture as subjects attempt to maintain normal rest patterns without environmental light cues. The typical progression through sleep stages becomes irregular, with REM sleep patterns showing particular sensitivity to altered light conditions. Mental health impacts emerge as seasonal affective disorders affect populations far from their normal geographic ranges. Regions experiencing 6 months of darkness report increases in depression, anxiety, and other mood disorders typically associated with winter conditions. Conversely, areas facing continuous daylight experience different psychological stresses related to hyperactivity and overstimulation. As weeks and months pass in this new temporal environment, some organisms begin showing signs of adaptation, while others face extinction from their inability to adjust to the altered day-night cycles. The biological clocks that have governed life for billions of years slowly begin the challenging process of recalibration, though many species lack the flexibility to survive the transition. In this world of eternal twilight, where day and night extend for seasons rather than hours, life learns to keep time by new rhythms, while struggling to maintain the biological processes that depend on the ancient dance between light and darkness that no longer marks the passage of Earth's days. How does a sea turtle, hatched on a beach in Florida, find its way across the entire Atlantic Ocean to the same feeding grounds near Portugal, where its ancestors have fed for millions of years? How does an Arctic tern navigate from the Arctic to Antarctica and back again, covering more than 70,000 kilometers in a single year without ever losing its way? The answer lies in navigation systems so sophisticated that they make human GPS technology seem primitive by comparison. Systems that have guided life across Earth's surface, through its oceans and across its skies for hundreds of millions of years, and systems that suddenly find themselves pointing toward destinations that no longer exist. The biological navigation systems that guide animal movement represent some of evolution's most remarkable achievements. These living compasses, star charts, and GPS systems operate with precision that has allowed species to traverse entire hemispheres, locate feeding grounds separated by thousands of kilometers, and return to breeding sites no larger than a single beach or grove of trees. The sudden disruption of Earth's rotation and magnetic field creates a crisis for these navigation systems that threatens to unravel migration patterns built over geological timescales. Magnetic navigation, perhaps the most sophisticated of these biological compass systems, depends on specialized cells and proteins that can detect Earth's magnetic field with extraordinary sensitivity. Magnetoreception, the ability to sense magnetic fields, has evolved independently in dozens of different animal groups, from bacteria to birds to marine mammals, suggesting how crucial this sense has been for survival and reproduction. In birds, magnetic sensing appears to involve two distinct mechanisms working together to provide both directional information and positional data. The first mechanism uses magnetite crystals found in specialized cells, often located in the upper beak region. These crystals, identical in composition to the magnetic mineral found in rocks, orient themselves according to Earth's magnetic field and provide information about magnetic direction through mechanical forces transmitted to nerve endings. The second mechanism, even more remarkable, appears to involve quantum mechanical processes in certain proteins within the bird's eyes. Special photoreceptor proteins called cryptochromes, when activated by light, create pairs of entangled electrons whose quantum states are influenced by magnetic fields. This quantum compass provides directional information that birds can literally see as patterns of light and shadow overlaid on their visual field. These two systems working together allow birds to navigate with remarkable precision across distances that span continents and oceans. The magnetite compass provides course information for long-distance travel, while the quantum compass offers fine-scale directional data for precise navigation to specific locations. The integration of these magnetic sensing systems with other navigational cues creates navigation capabilities that exceed any human-made technology. Sea turtles employ magnetic navigation in ways that reveal the extraordinary precision possible with biological systems. Young sea turtles imprint on the magnetic signature of their natal beach, memorizing the specific combination of magnetic field strength and inclination angle that characterizes their birthplace. This magnetic fingerprint allows them to return to the same stretch of coastline decades later to lay their own eggs. But sea turtles use magnetic information for more than just homing. They navigate across entire ocean basins using magnetic maps that correspond to geographic locations. The loggerhead turtles that hatch on beaches along the southeastern United States follow magnetic guideposts that direct them into the Gulf Stream current system, where they spend several years feeding and growing in the floating sargassum communities. Each stage of their journey depends on recognizing magnetic landmarks that correspond to geographic features and oceanic conditions. The turtles follow the Gulf Stream north along the American coast, then ride the North Atlantic current eastward toward Europe, eventually joining the Canary Current that carries them south along the African coast, before the North Equatorial Current brings them back across the Atlantic toward their starting point. This circular journey, known as the North Atlantic Gaia, takes several years to complete and requires the turtles to recognize dozens of magnetic waypoints along the route. Each waypoint corresponds to specific feeding opportunities, current characteristics, and habitat conditions that the turtles must identify correctly to survive the journey and eventually return to reproduce. Marine mammals demonstrate equally sophisticated magnetic navigation abilities adapted to their oceanic environment. Whales undertake some of the longest migrations in the animal kingdom, with some species traveling over 25,000 kilometers annually between feeding and breeding areas. These migrations follow routes that pass through deep oceanic basins where visual landmarks are non-existent and other navigation cues are minimal. The magnetic navigation systems of whales appear to be calibrated to detect not just magnetic direction and intensity, but also magnetic gradients that correspond to underwater topographic features. Sedamounts, underwater ridges, and deep ocean trenches each create distinct magnetic signatures that whales can use as navigational landmarks even in the featureless depths of the open ocean. Dolphins and other smaller cetaceans use magnetic navigation for coastal movements and for maintaining contact with social groups during hunting activities. The echolocation abilities that make these animals famous work effectively only over relatively short distances, but magnetic navigation allows them to maintain course over longer journeys and to coordinate group movements across areas where acoustic communication becomes difficult. Fish species employ magnetic navigation systems that guide both daily movements and seasonal migrations. Salmon use magnetic information as part of their remarkable ability to return to their natal streams after spending years in the open ocean. The magnetic signatures of different coastal regions provide large-scale guidance that brings returning salmon to the general vicinity of their home rivers, where chemical cues take over for the final approach to their specific spawning grounds. Even more remarkably, some fish species appear to use magnetic navigation to maintain their position within ocean currents. Tuna and other pelagic fish that spend their entire lives in the open ocean use magnetic cues to stay within optimal parts of ocean current systems, where feeding opportunities and water conditions remain favorable for their survival and reproduction. When Earth's rotation stops and the magnetic field begins its transformation, all of these navigation systems face disruption that threatens their basic functionality. The magnetic signatures that have guided animals for millions of years start changing at rates that exceed the ability of most species to adapt their navigation systems in real time. Migratory birds face immediate disorientation as their magnetic compasses begin pointing toward rapidly moving magnetic poles. The Arctic terns that normally migrate from Arctic to Antarctic regions following precise magnetic bearings find their compass headings shifting unpredictably. Birds that begin their migration following traditional magnetic routes discover that their compasses lead them away from familiar landmarks and toward geographic regions they have never encountered. The quantum compass system appears to be particularly sensitive to magnetic field changes. The cryptochromes that create quantum entangled electron pairs respond to magnetic field strength as well as direction, and the changing magnetic environment alters the visual patterns that birds use for navigation. The magnetic landscape that birds see overlaid on their visual field begins shifting in ways that make familiar territories appear foreign and navigational landmarks. Unrecognizable. Bird species that depend heavily on magnetic navigation for their long-distance migrations begin showing signs of navigational confusion within days of the magnetic field changes. Radar stations that monitor bird migration patterns record unusual flight behaviors, with flocks circling in apparent confusion or following erratic courses that bear no relationship to their traditional migration routes. Some bird species attempt to compensate by relying more heavily on other navigation cues, such as celestial navigation using the sun and stars, or geographical landmarks such as coastlines and mountain ranges. However, these alternative navigation systems evolved as supplements to magnetic navigation rather than replacements, and they lack the precision needed for the long-distance movements that many species require for survival. Sea turtles experience even more severe navigation disruption because their oceanic environment provides fewer alternative navigation cues than terrestrial or aerial environments. Young sea turtles that hatch during the period of magnetic field changes lose the magnetic signposts that should guide them into appropriate ocean current systems. Instead of following the magnetic cues that would lead them into the Gulf Stream or other current systems where they can find food and shelter, these young turtles become lost in oceanic regions that lack the floating sargassum communities and appropriate prey species they need for survival. The result is high mortality among juvenile sea turtles during their first year of life, when navigation errors have the most severe consequences for survival. Adult sea turtles attempting to return to nesting beaches find that their magnetic maps no longer correspond to geographic locations. Turtles that have successfully completed multiple migrations using magnetic navigation suddenly find themselves unable to locate the beaches where they were born and where they have previously nested successfully. Marine mammal populations face disruption of migration patterns that have remained stable for thousands of years. Whales that normally follow predictable routes between feeding and breeding areas begin showing altered migration timing and routes as their magnetic navigation systems provide conflicting information. Some populations attempt to continue their migrations using alternative cues, but these efforts often result in longer travel times and increased energy expenditure. The social structure of whale populations also faces disruption when magnetic navigation failures affect the ability of individuals to maintain contact with their groups during migration. Whale societies depend on coordinated movement patterns that require precise navigation by multiple individuals, and the breakdown of magnetic navigation systems threatens these social relationships. Smaller marine mammals such as dolphins face challenges in maintaining their normal ranges and territorial boundaries when magnetic landmarks lose their reliability. Coastal dolphin populations that normally move between specific feeding areas according to seasonal patterns find themselves unable to locate optimal hunting grounds that depend on precise geographical positioning. The disruption extends to fish populations whose spawning migrations depend on magnetic navigation. Salmon runs that have supported ecosystems and human communities for thousands of years begin showing irregularities as returning adults lose their ability to locate their natal streams accurately. The economic and ecological impacts of failed salmon runs affect entire river systems and the communities that depend on them. Ocean-dwelling fish species face changes in their ability to maintain optimal positions within current systems and to locate seasonal feeding grounds. Tuna populations that normally follow predictable migration routes begin dispersing more widely, affecting both the fish populations themselves and the fishing industries that depend on predictable catch locations. Marine ecosystems that depend on predictable animal movements begin experiencing cascading effects as predator-prey relationships lose their spatial and temporal coordination. Seabird colonies that depend on predictable fish aggregations find their food sources becoming less reliable as fish navigation patterns change. The economic impacts of navigation system failures affect industries that depend on predictable animal movements. Commercial fishing operations must adapt to changed fish distribution patterns, while wildlife tourism faces disruptions as animal viewing opportunities become less predictable. Conservation efforts face new challenges as protected area boundaries lose their relevance when animal populations can no longer navigate to traditional habitats. Marine protected areas established to safeguard critical habitats may no longer receive the species they were designed to protect if navigation systems fail to guide animals to these locations. Research programs studying animal migration must rapidly develop new methods for tracking and understanding altered movement patterns. The scientific understanding of animal navigation, built through decades of research on species with predictable movement patterns, requires fundamental revision as these patterns change in unprecedented ways. Rehabilitation centers begin receiving increased numbers of animals that appear to be lost or disoriented. Sea turtle rescue operations report growing numbers of individuals stranded far from appropriate habitats, while bird banding stations record unusual species compositions as migration routes shift unpredictably. Terrestrial navigation systems also face disruption as land-based animals lose magnetic guidance for their movements. Many mammals use magnetic information for navigation during daily foraging activities and seasonal movements between different habitats. The loss of reliable magnetic cues affects everything from the ability of bats to navigate during nightly foraging flights to the precision with which ground-dwelling mammals can return to their dens and territories. Domestic animals show signs of navigational confusion as their magnetic sensing abilities become unreliable. Homing pigeons, bred specifically for their exceptional navigation capabilities, begin showing reduced success rates in returning to their home locations. Dogs and cats that normally navigate familiar territories with confidence begin showing signs of disorientation during routine activities. The implications extend to human navigation systems that have traditionally relied on animal behavior as indicators of direction and weather patterns. Indigenous peoples who have used animal movement patterns and behavior as navigation aids find these traditional knowledge systems becoming unreliable as animal behavior changes unpredictably. Scientific research into animal navigation faces the challenge of studying systems that are changing faster than research programs can adapt. Long-term studies of migration patterns become historical records rather than ongoing research as the behaviors they document cease to exist in recognizable forms. The development of wildlife management strategies requires new approaches as traditional concepts of migration corridors and seasonal ranges become obsolete. Conservation planning must adapt to scenarios where animal movements follow patterns that have no historical precedent. As weeks and months pass, some populations begin showing signs of adaptation to the altered magnetic environment. Younger animals with more flexible nervous systems may develop new navigation strategies that combine multiple sensory inputs in different ways. However, many species lack the behavioral flexibility to adapt quickly enough to survive the transition period. The long-term consequences for animal navigation depend on the stability of the new magnetic field configuration and the ability of different species to recalibrate their navigation systems. Some populations may develop new migration routes and behaviors adapted to the changed conditions, while others may face local or global extinction if they cannot adapt to the loss of traditional navigation capabilities. Educational institutions begin developing new curricula to help people understand the importance of animal navigation systems and the cascading effects of their disruption. Museums create exhibits documenting the migration patterns that existed before the rotational cessation, preserving knowledge of biological navigation systems for future generations. The phenomenon reveals the intricate connections between planetary physics and biological systems, demonstrating how evolutionary adaptations that developed over millions of years can be disrupted by changes in fundamental planetary characteristics. The navigation crisis serves as a reminder of the complex relationships between life and the physical systems that support it. In this world where magnetic compasses spin wildly and ancient migration routes lead nowhere, the navigators that have crossed oceans and continents for millions of years must learn new ways to find their paths through a landscape where all the signposts have been moved and the maps no longer match the territory. The lost navigators of Earth face the ultimate test of adaptation as they attempt to maintain their epic journeys in a world that no longer provides the guidance systems upon which their species have depended throughout their evolutionary history. Along the equatorial coastlines of Ecuador, Kenya, and Indonesia, something subtle but profound begins to manifest in the moments after Earth's rotation ceases. A person standing at sea level near the equator, who moments before weighed exactly 70 kilograms, now finds themselves carrying an additional 200 grams of mass as Earth's gravitational embrace tightens imperceptibly. This tiny change, barely noticeable to human perception, represents the first whisper of a much larger transformation as our planet slowly begins to reshape itself into the form gravity has always preferred. The relationship between weight and gravity seems deceptively simple in our everyday experience, but the reality involves complex interactions between Earth's mass, its shape, and its rotation that have been locked in delicate balance for billions of years. Weight is not merely the attraction between our bodies and the planet beneath our feet. It is the result of gravitational force, minus the centrifugal effect created by Earth's rotation, which constantly attempts to fling everything on the surface into space. At Earth's equator, where the rotational velocity reaches its maximum of over 1600 kilometers per hour, the centrifugal force reduces the effective weight of objects by approximately 0.5% compared to what they would weigh on a non-rotating sphere. This reduction might seem negligible, but when multiplied across the mass of entire continents, oceans, and atmosphere, it represents forces capable of reshaping the planet itself. The disappearance of centrifugal force affects different latitudes with mathematical precision that follows the physics of rotation. At the poles, where rotational velocity approaches zero, the weight change remains minimal. But as one moves toward the equator, the effect increases according to the cosine of latitude, reaching maximum impact at 0 degrees latitude, where the centrifugal force had been strongest. This creates a gradient of weight change across Earth's surface that produces differential stresses in every structure, from the molecular level to continental scales. Buildings designed to support specific loads suddenly find their foundations experiencing marginally different stresses. The concrete and steel that form our cities must accommodate forces they were never calculated to bear. The human body itself becomes a microcosm of these gravitational changes. The inner ear, which maintains our sense of balance through fluid-filled chambers sensitive to acceleration, begins detecting the subtle alterations in gravitational force. While the weight change is too small for conscious perception, the vestibular system that governs balance and spatial orientation starts receiving signals that differ slightly from those it evolved to interpret. Blood circulation faces new challenges as the cardiovascular system adapts to marginally altered gravitational conditions. The heart, calibrated through millions of years of evolution to pump blood against Earth's standard gravitational field, must adjust its output to maintain proper circulation under the modified conditions. Blood pooling in the lower extremities changes subtly, affecting everything from blood pressure regulation to the body's fluid balance. Plants experience these gravitational changes through their gravitropic responses, the mechanisms that allow roots to grow downward and shoots to grow upward in response to gravity. The cells responsible for detecting gravitational direction, called statocytes, contain dense organelles that settle according to gravitational pull. The alteration in gravitational force, though small, begins affecting the precision of these cellular compasses. Trees, those ancient sentinels that have stood for centuries, begin experiencing differential stresses as their massive trunks and branches adjust to marginally altered gravitational loading. The wood fibers that provide structural support developed their strength characteristics under specific gravitational conditions, and even tiny changes in loading patterns can affect growth patterns and structural integrity over time. But the most profound consequences of altered gravitational conditions emerge not from the immediate weight changes, but from Earth's response to the elimination of centrifugal forces that have shaped its form for billions of years. Our planet is not the perfect sphere it appears to be from space. It is an oblate spheroid, flattened at the poles and bulging at the equator due to rotational forces. This equatorial bulge represents a difference of over 21 kilometers between Earth's equatorial and polar diameters. The excess material at the equator, accumulated over geological timescales, has been held in place by the centrifugal force created by rotation. With that force suddenly eliminated, gravity begins the long process of redistributing this excess mass toward a more spherical configuration. The redistribution process operates according to the principle that Earth, like any fluid body, will eventually assume the shape that minimizes its gravitational potential energy. For a non-rotating planet, this optimal shape is a perfect sphere, with all mass distributed as close as possible to the center of mass. The current oblate shape becomes gravitationally unstable without rotation to maintain it. This restructuring process begins immediately, but occurs over timescales that span decades to centuries, depending on the rheological properties of different parts of the planet. The crust, relatively rigid but still capable of slow deformation, begins experiencing stresses as the underlying mantle starts flowing toward new equilibrium positions. The ocean floors, bearing the enormous weight of seawater, begin adjusting to new pressure distributions as water starts migrating from equatorial regions toward polar areas. The continental shelves, shaped over millions of years by sea level changes and tectonic processes, face new patterns of loading and unloading as ocean levels redistribute. Mountain ranges experience altered stress patterns as gravitational forces redistribute. The Andes, stretching along South America's Pacific coast near the equator, begin experiencing differential gravitational loading that affects the balance of forces that have maintained their elevation for millions of years. The Himalayas, positioned further from the equator, experience different but equally significant changes in the gravitational environment that has shaped their development. Volcanic systems encounter modified conditions as magma chambers adjust to altered pressure gradients. The buoyancy forces that drive volcanic eruptions depend on the density differences between magma and surrounding rock, and these relationships change subtly as gravitational conditions shift. Some dormant volcanic systems might become more active, while others could experience reduced eruptive potential. The solid Earth's response to gravitational redistribution generates seismic activity unlike anything in recorded geological history. These are not the sudden violent earthquakes associated with tectonic plate movements, but rather the slow, continuous adjustments of a planet reshaping itself according to new gravitational imperatives. Gravity measurements, conducted by sensitive instruments at research stations worldwide, begin recording systematic changes in local gravitational acceleration. These changes, measured in millionths of Earth's surface gravity, provide real-time data about mass redistribution processes occurring throughout the planet's interior. The geoid, that imaginary surface representing mean sea level extended across continents, begins shifting as gravitational equipotential surfaces adjust to the new mass distribution. This affects the precision coordinate systems used for GPS navigation and surveying, requiring continuous recalibration of reference systems that assumed a stable gravitational field. Satellite orbits experience subtle alterations as Earth's gravitational field evolves. The gravitational anomalies created by mass redistribution affect spacecraft trajectories in ways that require frequent orbital corrections. GPS satellites, which provide positioning accuracy dependent on precise knowledge of their orbital positions, begin showing systematic errors that accumulate over time. The tidal forces exerted by the Moon and Sun interact differently with a planet that no longer rotates. While the basic tidal mechanism continues operating, the complex relationships between tidal forces and Earth's rotational response begin changing in ways that affect tidal patterns worldwide. Ocean tides lose some of their complexity as the Coriolis effect disappears, but they gain new characteristics from the altered gravitational field and changing ocean basin shapes. Tidal calculations based on mathematical models developed over centuries of observation require fundamental revision as the underlying assumptions about Earth's shape and gravitational field no longer apply. The International Network of Seismographic Stations begins recording new types of seismic signals associated with continuous crustal adjustment. These signals, characterized by extremely low frequencies and long durations, represent the acoustic signature of a planet settling into a new gravitational equilibrium. Underground mining operations face modified conditions as stress patterns in rock formations shift according to the new gravitational loading. Mine shafts and tunnels, designed for specific stress conditions, must be re-evaluated for safety under the altered gravitational environment. The measurement standards that define mass and weight face challenges as the fundamental gravitational reference frame changes. The kilogram, defined by reference to gravitational acceleration at specific locations, requires redefinition or adjustment as local gravity measurements drift from their historical values. Time measurement systems that depend on gravitational effects, such as atomic clocks sensitive to gravitational time dilation, begin showing systematic deviations as the gravitational potential at their locations changes. These changes are extraordinarily small but significant for systems requiring extreme temporal precision. The detection of gravitational waves, those ripples in space-time caused by accelerating massive objects, faces new challenges as Earth-based detectors adjust to modified gravitational backgrounds. The LIGO and Virgo detectors, designed to measure gravitational wave signals against the stable gravitational environment of rotating Earth, must recalibrate for operation in the altered gravitational field. Materials science encounters new phenomena as the mechanical properties of substances respond to marginally altered gravitational loading. Crystal growth processes, dependent on precise gravitational conditions, begin producing materials with subtly different characteristics. The semiconductor industry, relying on crystal structures with atomic scale precision, faces quality control challenges as growth conditions shift imperceptibly. Precision manufacturing processes that depend on gravitational references begin showing systematic errors. Level measurements, used throughout construction and manufacturing, require recalibration as the local gravitational vertical shifts with changing mass distributions. The biological effects of altered gravity, while subtle, begin affecting physiological processes that evolved under specific gravitational conditions. The otolith organs in the inner ear, responsible for detecting linear acceleration and gravitational orientation, start receiving signals that differ slightly from evolutionary expectations. Plant growth patterns begin showing modifications as gravitropic responses adapt to the marginally altered gravitational environment. Root systems, which grow toward the gravitational center, begin showing slight directional changes that accumulate over growing seasons. Tree trunks and branches begin exhibiting modified growth patterns as their gravitropic guidance systems adjust to new gravitational vectors. Fluid dynamics in both biological and technological systems experience subtle changes as convection patterns respond to altered gravitational acceleration. These changes affect everything from blood circulation patterns to the efficiency of heating and cooling systems that depend on natural convection for heat transfer. Research facilities studying fundamental physics encounter new experimental conditions as their precision instruments detect the ongoing changes in gravitational acceleration. Experiments designed to measure extremely small forces or accelerations must account for the gradually changing gravitational background. The field of geodesy, which studies Earth's shape and gravitational field, experiences a renaissance as researchers document the planet's transformation in real time. The mathematical models that describe Earth's shape and gravity field require continuous updating as the planet adjusts to its new rotational state. International standards organizations face the challenge of maintaining measurement consistency as the gravitational references that underlie many physical standards begin changing. The definition of weight-based measurements requires revision to account for the evolving gravitational environment. Educational institutions develop new curricula to help students understand the relationship between planetary rotation and gravitational effects. Physics textbooks require updates to reflect the real-world observations of gravitational field changes that were previously only theoretical considerations. The construction industry must adapt building codes and engineering standards to account for the gradually changing gravitational environment. While the changes are small, they accumulate over time and affect the long-term stability of structures designed for specific gravitational loads. Transportation systems experience subtle effects as the altered gravitational field affects everything from fuel efficiency calculations to the behavior of suspended loads. Airlines must adjust flight performance calculations, while shipping companies adapt cargo loading procedures to account for marginally different weights at various latitudes. Agricultural systems encounter new growing conditions as plant gravitropic responses adapt to altered gravitational cues. Crop yields may change subtly as root development and nutrient uptake patterns adjust to the modified gravitational environment. Weather pattern modeling requires updates as atmospheric circulation models incorporate the effects of altered gravitational acceleration on air density and pressure patterns. While these effects are small, they can influence long-term climate predictions and weather forecasting accuracy. Financial markets respond to the implications of gravitational changes for industries dependent on precise measurements and standards. Insurance companies reassess risks associated with structural failures and equipment malfunctions caused by unexpected gravitational loading changes. Scientific instrument manufacturers develop new calibration procedures and reference standards to maintain accuracy in the changing gravitational environment. Precision scales, accelerometers, and other gravity-sensitive instruments require continuous recalibration to maintain their specified accuracy. The space industry adapts launch calculations and orbital mechanics models to account for the altered gravitational field. Satellite deployment and space mission planning require updated mathematical models that reflect the planet's changing gravitational characteristics. As months and years pass, Earth slowly assumes a more spherical shape as gravitational forces redistribute mass from equatorial regions toward polar areas. This process, imperceptible to human observation but detectable by sensitive instruments, represents one of the most fundamental changes in our planet's physical structure since its formation billions of years ago. The weight of stillness reveals itself not in dramatic immediate changes, but in the patient, inexorable force of gravity reclaiming a planet that no longer spins, redistributing mass according to principles that have governed celestial mechanics since the formation of the solar system, and creating a new Earth where gravity's full embrace is felt without the opposing force of rotation that has defined our world throughout all of recorded history. At 3 o'clock on a Tuesday afternoon, the financial district of Tokyo hums with its usual precision elevators carrying thousands of people between floors, bullet trains arriving at Shinjuku Station with clockwork regularity, and construction cranes swinging steel beams into position on the newest skyscraper projects. In this moment of ordinary urban complexity, Earth suddenly stops rotating, and the forces of physics transform the most advanced human settlements into landscapes of unprecedented destruction, revealing how precariously our civilization balances on the stable foundation of planetary motion. The urban environment represents humanity's most complex creation, where millions of people live and work within intricate networks of buildings, transportation systems, and infrastructure. These systems evolved, assuming Earth's rotation would continue unchanged, with every structure designed according to engineering principles that take rotational forces for granted. When the planet stops spinning, cities become testing grounds for physics experiments no engineer ever imagined. Tokyo, situated at approximately 35 degrees north latitude, experiences rotational velocity of about 1,300 kilometers per hour. When this motion suddenly ceases, everything in the city continues eastward at that tremendous speed, while the ground beneath stops moving. The result transforms the urban landscape into a horizontal projectile physics problem of unprecedented scale. Skyscrapers face forces no structural engineer calculated during their design. These towers, engineered to flex with wind loads and seismic activity, suddenly experience horizontal accelerations that exceed their design specifications by orders of magnitude. The contents of every building become projectiles, traveling at highway speeds through interior spaces never intended to contain such energies. Office buildings transform into launching mechanisms for their furnishings. Desks, computers, filing cabinets, and people accelerate eastward through windows, walls, and structural elements that provide no resistance to forces of such magnitude. The 20th floor of any high-rise building becomes a horizontal cannon, firing its contents across the city at speeds that turn everyday objects into devastating projectiles. The Tokyo Skytree, that 634-meter tower, designed to withstand earthquakes and typhoons, faces structural loads it was never engineered to bear. The observation decks, normally offering panoramic views of the city, become launching platforms for tourists and equipment hurled eastward at velocities that make survival impossible. Transportation systems collapse instantly across multiple domains. The Shinkansen bullet trains, traveling at their normal operating speeds when rotation ceases, suddenly find themselves moving relative to tracks that are no longer moving beneath them. Passengers inside these trains experience the combined effects of the train's original velocity plus the eastward motion from rotational inertia. The physics of this collision between moving objects and suddenly stationary infrastructure creates forces that exceed all engineering safety factors. Train cars designed to protect passengers during derailments at normal speeds cannot contain the energies involved when a 300 km/h train encounters the effects of 1300 km/h rotational cessation. Subway systems face differential destruction based on their depth and orientation. Surface-level stations experience the full force of atmospheric winds and projectile debris, while deep underground stations provide some protection from surface chaos. However, tunnels aligned east-west experience differential forces as their eastern and western ends face different atmospheric pressures and debris loads. The Tokyo Metropolitan Expressway system becomes a network of horizontal launching ramps. Vehicles traveling on elevated sections find themselves airborne as the roadway structures beneath them experience forces beyond their design limits. Traffic jams become scenes of unprecedented destruction as hundreds of vehicles become projectiles moving at combined velocities that exceed anything in automotive safety testing. Airport operations face complete failure as aircraft on the ground experience wind speeds that exceed their maximum design tolerances. Planes parked at terminals become projectiles that destroy terminal buildings, while aircraft in flight encounter atmospheric conditions that make controlled landings impossible, on runways experiencing supersonic ground winds. Haneda Airport, one of the world's busiest aviation hubs, transforms from a transportation center into a debris field as aircraft of every size become uncontrolled missiles. The control tower, designed to withstand typhoon winds, cannot survive the forces generated by aircraft moving at rotational plus atmospheric velocities. The Port of Tokyo, one of the world's busiest container facilities, transforms into a scene of maritime chaos as cargo ships experience wave conditions unlike anything in nautical engineering. Container cranes, those massive structures designed to load and unload ships, become launching mechanisms for shipping containers that achieve velocities dangerous to anything in their path. Ships moored at docks suddenly find themselves experiencing relative motion as the water they float in continues moving eastward while the docks remain stationary. The kinetic energy involved in a fully loaded cargo ship moving at 1300 km/h relative to its berth creates forces that destroy port facilities and generate tsunamis within enclosed harbour areas. Power generation and distribution systems face cascading failures as transmission towers experience wind loads that exceed their structural capacity by enormous margins. The electrical grid that powers the city collapses within minutes, as towers topple in predictable patterns determined by wind direction and structural orientation. Nuclear power plants in the Greater Tokyo region face emergency conditions no safety protocol anticipated. Reactor buildings designed to contain radioactive materials under extreme conditions encounter external forces that test every containment system simultaneously. Emergency cooling systems face challenges when the infrastructure that supports them experiences destruction from unprecedented external forces. Water supply systems fail as treatment facilities and pumping stations experience structural damage from wind-borne debris. The complex network of pipes, reservoirs, and distribution systems that supply water to millions of people faces disruption that affects every aspect of urban life. Water pressure drops to zero as pumping stations lose power and physical integrity simultaneously. Sewage treatment facilities encounter similar destruction, creating public health emergencies that compound the immediate physical dangers. The biological and chemical processes that safely treat urban waste require precise environmental controls that become impossible to maintain when facilities face structural destruction and power failures. Communication networks collapse as cell towers become projectiles and fiber optic cables snap under differential stresses. The internet infrastructure that connects Tokyo to the global economy disappears within hours as data centers experience conditions that destroy sensitive electronic equipment despite their hardened designs. The massive data centers that support cloud computing services and financial transactions lose both their physical infrastructure and their electrical power simultaneously. Server farms designed with multiple redundancy systems cannot function when the buildings that house them experience forces that turn computer equipment into debris. Emergency services face conditions that overwhelm their capacity to respond. Fire departments cannot operate in wind speeds that ground their aerial equipment and make ground operations extremely dangerous. The water supply failures that affect the entire city eliminate the resources firefighters need to combat the numerous fires that start when electrical systems fail catastrophically. Police and emergency medical services lose their mobility as transportation networks become impassable and communication systems fail. Hospitals encounter patient loads that exceed their capacity while simultaneously losing their ability to function normally due to power failures and structural damage. Medical facilities designed to operate during natural disasters face conditions that make normal operations impossible, while treating injuries of types and scales never encountered in medical training. Operating rooms become unusable when buildings lose structural integrity, while emergency generators fail when fuel storage systems are destroyed by debris. The residential areas surrounding Tokyo's center experience destruction that varies according to building construction and local topography. Traditional Japanese wooden construction, designed to flex during earthquakes, proves inadequate for the horizontal forces generated by sudden rotational cessation. Modern concrete and steel residential towers face the same projectile problems as commercial high-rises, but with different implications for urban planning and evacuation. Residential buildings contain different types of objects and materials that become projectiles with different flight characteristics and destructive potential. Shopping districts and commercial areas become dangerous mazes of debris as storefronts fail and their contents become wind-borne projectiles. The famous Shibuya crossing, normally a symbol of urban order and precision, becomes impassable as buildings surrounding the intersection lose their structural integrity and contribute debris to the atmospheric chaos. The neon signs and electronic billboards that characterize Tokyo's commercial districts become particularly dangerous projectiles due to their aerodynamic properties and electrical components. These objects, designed to capture attention through size and placement, become massive flying hazards that add to the destruction of street-level infrastructure. Cultural landmarks face destruction that erases centuries of architectural heritage within hours. Buddhist temples and Shinto shrines, some over 1,000 years old, encounter forces that their traditional construction methods cannot resist. The imperial palace, protected by massive stone walls and traditional architecture, provides some shelter but cannot escape the general destruction affecting the entire metropolitan area. The traditional Japanese architecture that has survived earthquakes and typhoons for centuries faces forces for which it was never designed. The flexible wood and paper construction that allows buildings to sway safely during seismic events cannot withstand the horizontal forces generated by objects moving at highway speeds. Public transportation hubs become scenes of particular devastation as their large open spaces and complex structural systems experience forces that exceed all design parameters. Tokyo Station, Shinjuku Station, and other major terminals transform from transportation nodes into debris-filled areas impassable to human movement. These stations, designed to handle millions of passengers daily through carefully engineered crowd flow patterns, become death traps when their structural systems fail and their contents become projectiles. The underground commercial districts associated with major stations face their own challenges as ventilation systems fail and debris blocks emergency exits. Underground commercial districts and subway malls provide some protection from surface-level destruction, but face their own challenges as ventilation systems fail and emergency egress routes become blocked by surface debris. The underground cities that exist beneath major stations become temporary shelters for those fortunate enough to be below ground when the rotation stops. The complex systems that provide lighting, air circulation, and climate control to underground spaces fail when surface infrastructure is destroyed. These underground refuges become increasingly difficult to sustain as their life support systems lose power and connection to surface resources. The economic consequences begin immediately as the financial district faces physical destruction that eliminates the infrastructure supporting one of the world's major economic centers. Banks, trading floors, and corporate headquarters disappear beneath debris loads that make recovery operations impossible for months or years. The Tokyo Stock Exchange, representing trillions of dollars in market capitalization, becomes physically inaccessible as the building that houses it experiences structural failure. The computer systems that execute millions of financial transactions daily are destroyed along with the infrastructure that supports them. Manufacturing facilities throughout the Tokyo metropolitan area face equipment destruction that eliminates production capacity for industries essential to global supply chains. Semiconductor fabrication plants, automotive assembly lines, and precision manufacturing facilities encounter contamination and equipment damage that requires complete reconstruction rather than repair. The just-in-time manufacturing processes that characterize Japanese industry face complete disruption as the transportation networks that support them become unusable. Part suppliers, assembly plants, and distribution centers lose their ability to coordinate production when communication and transportation systems fail simultaneously. The port facilities that handle much of Japan's international trade become inoperable as cranes topple and container storage areas become scenes of destruction. The logistics networks that support just-in-time manufacturing and global commerce face disruption that affects economic systems far beyond Japan's borders. Container ships waiting to unload at Tokyo's ports find their cargo scattered across port facilities by forces that turn shipping containers into projectiles. The supply chain disruptions affect manufacturing and retail operations worldwide, as critical components and finished goods fail to reach their destinations. Scientific research facilities, including universities and corporate laboratories, lose decades of research as equipment destruction, eliminates irreplaceable experimental setups and data storage systems. The knowledge infrastructure that supports technological advancement faces setbacks that affect global scientific progress. Research institutions housing particle accelerators, astronomical observatories, and advanced manufacturing equipment lose not only their physical facilities, but also the expertise and institutional knowledge required to rebuild such complex systems. Graduate students, postdoctoral researchers, and faculty face the loss of years or decades of research progress. As hours pass after the initial destruction, the scale of urban system failure becomes apparent. Cities designed as integrated networks of mutually dependent systems face cascading failures that affect every aspect of urban life. The complexity that makes modern cities possible becomes their vulnerability when the fundamental assumptions about planetary motion prove incorrect. The Tokyo metropolitan area, home to nearly 40 million people, becomes a case study in urban vulnerability to forces beyond human experience. The same density and interconnectedness that create urban efficiency become sources of destruction when systems designed for stability encounter the physics of a planet that no longer rotates. Recovery efforts face challenges unlike those encountered in any previous disaster. The scale of destruction exceeds the capacity of any emergency response system, while the simultaneous failure of transportation, communication, and utility systems eliminates the infrastructure necessary for coordinated disaster response. The international nature of modern cities means that the destruction of Tokyo affects global systems in ways that extend far beyond Japan's borders. Financial markets, supply chains, and communication networks worldwide experience disruptions as one of the world's major urban centers becomes temporarily uninhabitable. Emergency response teams from around the world face challenges in reaching the affected area when airports and seaports become unusable and communication systems fail. The international cooperation required for disaster response of this scale requires infrastructure and coordination mechanisms that the disaster itself has destroyed. In this transformed urban landscape, the cities that represented humanity's triumph over natural forces become evidence of our dependence on planetary systems we rarely consider, revealing the fragile balance between human civilization and the cosmic forces that have shaped our world throughout history. The urban environment that supported millions of people and trillions of dollars in economic activity transforms into a stark reminder of the physical forces that govern planetary motion and the vulnerability of human systems to changes in those fundamental forces. Hurricane formation requires a precise combination of warm ocean water, atmospheric instability, and the Coriolis effect to create the rotating wind patterns that concentrate enormous energies into devastating cyclonic systems. Without Earth's rotation, this final crucial ingredient disappears, making it physically impossible for hurricanes, typhoons, and cyclones to form, regardless of how favorable other atmospheric conditions might become. In a world without rotation, the great spinning storms that have shaped weather patterns and coastal evolution for millions of years simply cannot exist. The death of rotating storms represents more than just the elimination of particular weather phenomena. It signals the complete reorganization of Earth's energy distribution systems. Hurricanes serve as massive heat engines that transport thermal energy from tropical oceans toward higher latitudes, helping to moderate global temperature differences. Without these systems, the planet must find entirely new ways to balance the energy received from solar heating. Weather systems that depend on rotational forces face immediate dissolution as the Coriolis effect vanishes. The great cyclonic and anticyclonic systems that dominate weather patterns worldwide lose the rotational component that maintains their structure. High-pressure systems stop rotating and begin spreading outward in simple radial patterns, while low-pressure areas become zones of vertical convection without the spiral inflow patterns that characterize rotating storms. The jet streams, those fast-moving rivers of air that guide weather systems across continents and oceans, begin straightening from their characteristic meandering patterns. Without Coriolis forces to deflect moving air masses into curved trajectories, these high-altitude winds start following more direct paths determined solely by pressure gradients and thermal differences. This straightening process fundamentally alters global weather patterns as the jet streams no longer create the loops and waves that bring different air masses into contact across continents. The polar jet stream, normally responsible for bringing Arctic air southward in winter and moderating summer temperatures, transforms into a more direct east-west flow that lacks the variability that has characterized temperate climate patterns. New forms of severe weather emerge to replace the rotating storms that no longer form. Linear storm systems develop along frontal boundaries where different air masses meet, creating bands of thunderstorms that extend across entire continents, rather than the circular patterns of traditional cyclonic systems. These linear storms distribute their energy across much broader areas, but can maintain severe weather conditions for extended periods. The energy that would have been concentrated into rotating hurricanes now spreads across vast linear storm complexes that create different types of weather hazards. Instead of intense winds concentrated in small areas, these systems produce moderate but persistent winds across regions thousands of kilometers wide, creating challenges for which no weather forecasting or emergency management system was designed. Atmospheric circulation patterns reorganize around purely thermal principles as temperature differences between equatorial and polar regions drive new forms of convection. Without rotation to create the complex three-cell circulation systems in each hemisphere, the atmosphere develops simpler but more direct circulation patterns that transport heat through different mechanisms. The Hadley cell circulation, normally confined to tropical regions, expands poleward as rising equatorial air spreads directly toward both poles without being deflected by Coriolis forces. This creates a single massive convection cell in each hemisphere that replaces the complex interaction between Hadley, Ferrel, and polar cells that has characterized atmospheric circulation throughout Earth's history. The absence of hurricane season eliminates one of the most predictable aspects of tropical meteorology. Coastal communities that have adapted to seasonal hurricane threats over thousands of years face new weather patterns that follow different rules and timing. The economic systems built around hurricane preparation and recovery must adapt to weather threats that operate according to different principles. Insurance companies face the challenge of assessing weather-related risks when the historical data upon which their models depend becomes irrelevant. Hurricane risk models, refined through decades of statistical analysis, provide no guidance for evaluating risks from linear storm systems that operate according to different physical principles. Ocean-atmosphere interactions lose the rotating component that has driven marine weather systems throughout geological history. The formation of waterspouts, those tornado-like vortices that develop over water surfaces, becomes impossible without the rotational forces necessary to concentrate vorticity into tight spiral patterns. Tropical cyclones, which normally form over warm ocean waters when atmospheric conditions favor rotation, find their formation mechanism eliminated even when sea surface temperatures and atmospheric instability provide abundant energy for storm development. The vast amounts of energy that would have powered these rotating systems must find alternative expression through non-rotational convective processes. Monsoon systems undergo fundamental changes as their seasonal patterns lose the rotational component that has driven their characteristic circulation patterns for millions of years. These massive seasonal wind shifts, which bring life-giving rains to billions of people, transform from rotating systems into direct thermal circulations between heated land masses and cooler ocean areas. The Indian monsoon, crucial for agriculture across South Asia, loses the rotating circulation patterns that normally bring moisture from the Indian Ocean across the subcontinent. Instead of the complex seasonal reversal of wind patterns that characterizes traditional monsoon behavior, the region experiences more direct thermal circulation that may provide moisture through different mechanisms and timing. The energy that once drove hurricane formation remains in the climate system but expresses itself through different mechanisms. Temperature differences between ocean and land areas create more direct convective systems that transport heat and moisture through linear rather than circular patterns, affecting regional climate in ways that have no precedent in meteorological records. Without hurricanes to mix ocean waters and redistribute heat within oceanic basins, sea surface temperatures begin developing different patterns. The ocean mixing that hurricanes normally provide through their passage must be replaced by other mechanisms, potentially leading to more stratified ocean conditions and different patterns of marine productivity. The upwelling and mixing caused by hurricane passage, which brings nutrients from deep waters to the surface and supports marine ecosystems, disappears from oceanic processes. Coastal marine environments that depend on hurricane-driven mixing for nutrient cycling face changes in water chemistry and biological productivity. Weather prediction faces fundamental challenges as computer models developed to forecast rotating storm systems prove inadequate for predicting weather patterns that follow different physical principles. Meteorological knowledge built through centuries of observing rotational weather systems requires complete revision for a world where such systems cannot form. The mathematical equations that govern atmospheric behavior remain valid, but their solutions produce entirely different weather patterns when the rotation term becomes zero. Meteorologists must develop new conceptual frameworks for understanding weather systems that operate without the Coriolis effect that has been central to atmospheric science. The formation of tornadoes, those intense rotating columns of air that develop within severe thunderstorms, also becomes impossible without the rotational forces necessary to concentrate atmospheric vorticity. The Great Plains of North America, famous for tornado activity, experience different types of severe weather as the atmospheric dynamics that create tornado-producing supercells no longer operate. Tornado Alley, that region of the central United States where atmospheric conditions normally favor tornado formation, experiences linear severe weather systems instead of the rotating supercells that produce tornadoes. These linear systems create different types of wind damage patterns that affect emergency management and building design considerations. Extratropical cyclones, those large-scale storm systems that bring much of the precipitation to mid-latitude regions, lose their rotating structure and transform into linear frontal systems. The complex occlusion processes that characterize mature cyclonic systems no longer occur, simplifying storm structure but altering precipitation patterns and intensity distributions. Winter storms that normally develop as rotating low-pressure systems begin following linear patterns that create different snowfall distributions. Instead of the spiral bands of precipitation that characterize nor'easters and other rotating winter storms, snow falls in linear bands that may cover different geographic areas with different accumulation patterns. The seasonal patterns that govern agriculture and ecosystem timing lose the hurricane and typhoon influences that have helped determine growing seasons and precipitation timing for thousands of years. Agricultural systems must adapt to weather patterns that lack the seasonal regularity provided by rotating storm systems. Plant breeding and crop selection programs face challenges as the weather patterns that crops were selected to tolerate no longer exist. Rice varieties adapted to typhoon conditions, corn varieties bred for hurricane-prone regions, and other agricultural genetics require re-evaluation for weather patterns that follow new rules. Coastal erosion patterns change as the wave action generated by offshore storms follows different patterns. Hurricane-generated waves, which can travel thousands of kilometers from storm centers, no longer shape coastlines in the dramatic ways that have carved shoreline features throughout geological history. Beach nourishment and coastal protection systems designed around hurricane wave patterns require redesign for wave conditions generated by linear storm systems. The engineering calculations that determine seawall heights and beach profile designs lose their foundation when the storm systems that generate coastal waves change fundamentally. Climate zones begin shifting as the heat transport mechanisms change from rotating storm systems to linear convective processes. The boundaries between different climate types, traditionally influenced by the tracks of rotating storms and their associated weather patterns, start migrating to new locations determined by direct thermal gradients. Tropical climate zones, normally characterized by seasonal hurricane activity, develop new weather patterns based on direct thermal convection between heated land areas and warm ocean surfaces. These new patterns may provide moisture through different mechanisms that affect vegetation types and ecosystem characteristics. The upper atmosphere experiences different circulation patterns as the high altitude winds associated with hurricane outflow no longer create the complex flow patterns that have influenced stratospheric circulation for millions of years. These changes affect the transport of trace gases and aerosols through the upper atmosphere. Stratospheric circulation, normally influenced by the pumping action of hurricanes that inject moisture and energy into the upper atmosphere, develops new patterns based on direct thermal convection. This affects ozone distribution, atmospheric chemistry, and the filtering of solar radiation. Weather modification efforts lose one of their primary targets as hurricane suppression research becomes irrelevant in a world where such storms cannot form. Cloud seeding and other weather modification techniques must focus on the linear storm systems that replace rotating weather patterns. Atmospheric research programs developed around hurricane investigation must redirect their focus to understanding linear convective systems. Hurricane hunter aircraft, satellite monitoring systems, and coastal radar networks require new missions focused on different types of weather phenomena. Emergency management systems developed around hurricane preparedness must completely restructure to address the different types of severe weather that emerge in the new atmospheric regime. The seasonal timing, geographic patterns, and intensity characteristics of severe weather all change in ways that require new approaches to public safety and disaster preparation. Evacuation planning, shelter design, and emergency supply distribution systems all require revision for weather threats that operate according to different principles. The coastal focus of hurricane preparedness expands to inland areas that may experience severe weather from linear storm systems. The insurance industry faces the challenge of assessing risks for weather patterns that have no historical precedent. Hurricane risk models developed through decades of statistical analysis become obsolete, while new models must be created for weather systems that operate according to different principles. Catastrophe modeling, the mathematical techniques used to assess weather-related insurance risks, requires fundamental revision as the rotating storms that drove much of weather-related insurance losses disappear from risk calculations. Scientific research into severe weather phenomena must redirect focus from rotating storm systems to the linear and convective systems that replace them. Decades of research into hurricane dynamics becomes historical knowledge, while new research programs develop understanding of non-rotational severe weather. Atmospheric science education requires new curricula that emphasize linear convective processes over rotating storm dynamics. Meteorology textbooks need complete revision to reflect atmospheric behavior in a world without Coriolis effects. International weather monitoring systems lose the rotating storm tracks that have provided predictable patterns for global weather forecasting. The World Meteorological Organization must develop new classification systems and monitoring protocols for weather patterns that follow different organizational principles. Weather station networks designed around hurricane tracking require new configurations focused on monitoring linear storm systems that may affect much larger geographic areas with different intensity patterns. As months and years pass in this new atmospheric regime, the planet develops alternative mechanisms for distributing the energy that hurricanes once transported. The climate system demonstrates its ability to establish new equilibrium patterns, but these operate according to principles that create weather patterns unlike anything in Earth's previous atmospheric history. Regional climate patterns adapt to the absence of hurricane-driven heat transport through the development of more persistent linear convective systems that provide similar energy redistribution through different mechanisms. Ocean currents and atmospheric circulation adjust to compensate for the missing rotational component of energy transport. The storms that cannot be leave behind a world where weather follows simpler rules but creates conditions that challenge every assumption about atmospheric behavior, forcing humanity and all life to adapt to weather patterns that operate without the rotating forces that have shaped climate throughout the history of our spinning world. In this transformed atmosphere, linear replaces circular direct thermal gradients, replace complex rotational dynamics, and the predictable seasonal patterns of rotating storms give way to weather systems that operate according to entirely new principles. Imagine a planet where one hemisphere basks in eternal summer under a sun that never sets, while the opposite side endures perpetual winter in darkness that never lifts. This stark division represents the ultimate destiny of Earth, when rotation ceases, creating a world split, not by political boundaries or geographic features, but by the fundamental forces of solar heating and radiative cooling that operate without the moderating influence of day-night cycles to distribute their effects across the planet's surface. The hemisphere facing the sun experiences continuous solar heating that transforms familiar landscapes into environments unlike anything in Earth's climatic history. Without the relief of nighttime cooling, temperatures rise continuously until they reach equilibrium between incoming solar radiation and outgoing thermal radiation. This equilibrium occurs at temperatures far exceeding anything experienced during normal summer conditions. Solar energy, concentrated on one hemisphere without interruption, creates surface temperatures that approach those found in Earth's hottest deserts, but sustained indefinitely across entire continents. The Sahara Desert, which normally experiences temperature relief during nighttime hours, becomes representative of conditions across half the planet's surface area. Meanwhile, the hemisphere facing away from the sun loses heat continuously through radiation to space without any solar input to replace the lost energy. Temperatures plummet toward levels that approach the radiative temperature of deep space, creating conditions more extreme than any winter in Earth's geological record. The dark hemisphere experiences cooling rates limited only by the thermal properties of air, water, and rock. Without atmospheric circulation to transport heat from the sunny side, temperatures drop toward the freezing points of atmospheric gases, creating conditions similar to those found on planets in the outer solar system. The boundary between these two extreme climate zones becomes a region of unprecedented weather activity as hot air from the sunlit hemisphere meets frigid air from the dark side. This boundary zone experiences continuous storm activity as thermal gradients drive weather systems unlike any previously observed on Earth. The terminator line, that boundary between day and night that normally sweeps around Earth every 24 hours, becomes a stationary zone of perpetual twilight. This twilight zone experiences the most moderate temperatures on the planet, as it receives oblique sunlight while also radiating heat to space. Climate patterns reorganize around the simple geometry of a planet with one hot hemisphere and one cold hemisphere and one cold hemisphere, eliminating the complex seasonal and latitudinal climate variations that have characterized Earth throughout its history. Weather systems develop along this day-night boundary, creating a ring of perpetual storms that circles the planet. The Coriolis effect, absent on the non-rotating Earth, no longer deflects air movements into the familiar spiral patterns that characterize weather systems on a spinning planet. Instead, air flows directly from high-pressure areas toward low-pressure regions, creating linear weather patterns that stretch across entire hemispheres. The hydrological cycle transforms as water evaporates continuously from the sunlit hemisphere and precipitates continuously in the dark hemisphere. This creates a one-way transfer of water from the hot side to the cold side, gradually changing the distribution of surface water across the planet. Oceans on the sunny hemisphere experience evaporation rates that exceed precipitation, causing sea levels to drop as water vapor migrates toward the dark hemisphere where it condenses and falls as snow or rain. This redistribution continues until equilibrium establishes between evaporation and the return flow of water through atmospheric circulation. Rivers on the sunny hemisphere gradually dry up as their sources disappear through evaporation, and their flow is not replenished by local precipitation. The Amazon River, the Nile, and other major river systems face elimination as the water cycle operates on a global rather than regional scale. Ecosystems face challenges as plants and animals adapted to regular temperature cycles encounter conditions that remain stable for months and years. The sunlit hemisphere experiences drought conditions as continuous heating evaporates surface water faster than precipitation can replace it, while the dark hemisphere becomes increasingly cold and dry as water freezes and remains frozen. Vegetation patterns adapt to the new climate reality, with plant communities migrating toward the twilight zone, where temperatures remain within tolerable ranges. Forests retreat from both the extremely hot and extremely cold regions, concentrating in narrow bands around the day-night boundary. Agricultural systems collapse as crop plants lose the temperature variations they require for normal growth and reproduction cycles. The growing seasons that have supported human civilization disappear, replaced by permanent conditions that support neither traditional agriculture nor natural ecosystem function. Wheat, rice, corn, and other staple crops require specific temperature cycles for germination, growth, flowering, and seed production. Continuous high temperatures prevent normal plant development, while continuous cold prevents growth entirely, forcing agriculture to concentrate in the narrow twilight zone. Human populations face migration pressures, as large areas of the planet become uninhabitable due to extreme temperatures. The temperate zones that have supported most of human civilization shrink to narrow bands along the day-night boundary, where temperatures remain within tolerable ranges. Cities located in the sunny hemisphere face abandonment as temperatures exceed human survival thresholds. Urban heat island effects, normally moderated by nighttime cooling, compound the solar heating to create surface temperatures that make outdoor activity impossible. The dark hemisphere cities face different but equally severe challenges as temperatures drop below freezing and remain there indefinitely. Heating systems designed for seasonal winter conditions cannot cope with permanent winter temperatures that continue dropping towards space-like conditions. The ocean circulation patterns reorganize around the temperature difference between hot and cold hemispheres rather than the complex circulation patterns driven by rotation and seasonal heating. The thermohaline circulation that normally drives global ocean currents transforms into a simpler pattern driven by the temperature gradient between hemispheres. Marine ecosystems adapt to the new ocean circulation patterns and temperature distributions. Fish populations migrate toward the twilight zones, where temperatures remain suitable for their survival, while polar and tropical species face habitat loss as their preferred temperature ranges disappear from large areas of the ocean. Coral reefs, adapted to specific temperature ranges in tropical waters, face extinction in the continuously heated waters of the sunny hemisphere. The symbiotic algae that provide corals with nutrients cannot survive the extreme temperatures that develop without nighttime cooling. Ice formation patterns change dramatically as the dark hemisphere accumulates ice continuously, while the sunny hemisphere loses all ice coverage. The polar ice caps, normally balanced between summer melting and winter accumulation, either grow continuously or disappear entirely depending on their location. Antarctica, if located in the dark hemisphere, becomes a massive ice accumulator as water vapor from the sunny hemisphere condenses and freezes on its surface. The Antarctic ice sheet grows to unprecedented size as it receives water from global evaporation without experiencing seasonal melting. Atmospheric chemistry changes as photochemical reactions occur continuously in the sunny hemisphere, while chemical preservation dominates in the frozen dark hemisphere. Ozone production and destruction patterns shift to follow the permanent day-night division rather than seasonal and latitudinal patterns. The jet streams, no longer guided by Coriolis forces and seasonal temperature variations, reorganize around the simple thermal gradient between hot and cold hemispheres. These new atmospheric circulation patterns transport heat and moisture according to direct thermal gradients, rather than the complex patterns characteristic of a rotating planet. Seasonal patterns disappear entirely as each location experiences constant conditions rather than the cyclical variations that have characterized Earth's climate throughout its history. The concept of seasons becomes meaningless in a world where each point on the surface experiences unchanging conditions. Plant and animal life cycles, evolved around seasonal timing cues, must adapt to constant environmental conditions or face extinction. Migration patterns, reproductive cycles, and hibernation behaviors all require fundamental revision in a world without seasonal change. The aurora phenomena, normally confined to polar regions due to Earth's magnetic field geometry, develop new patterns as the magnetic field itself changes in response to altered core dynamics. The interaction between solar wind and Earth's magnetic field creates new types of atmospheric displays. Tidal patterns simplify as the moon and sun create tides on a planet that no longer rotates beneath them. The complex tidal patterns caused by Earth's rotation disappear, replaced by simpler tidal motions that follow the gravitational influences more directly. Coastal areas experience new tidal patterns as the ocean responds to gravitational forces without the complicating effects of rotational motion. Some coastal regions experience higher tides, while others see reduced tidal ranges as the global tidal pattern reorganizes. Air pressure patterns develop according to the thermal differences between hemispheres, rather than the complex pressure systems associated with rotating weather patterns. Barometric pressure becomes primarily dependent on temperature, with continuous high pressure over the cold hemisphere and low pressure over the hot hemisphere. Wind patterns follow the pressure gradients directly from high to low pressure areas without the deflection caused by Coriolis forces. This creates consistent wind directions that flow from the cold hemisphere toward the hot hemisphere at the surface, with return flow at higher altitudes. The development of weather forecasting for a divided Earth requires completely new approaches, as the familiar patterns associated with rotating weather systems no longer apply. Meteorologists must develop new models based on thermal gradients rather than rotational dynamics. Climate science faces fundamental revision as researchers study a planet where climate zones are determined by position relative to the Sun rather than latitude and seasonal patterns. The complex climate classifications developed for a rotating Earth become obsolete in a world with simple thermal divisions. Human adaptation to the divided Earth requires technological solutions for surviving in both extremely hot and extremely cold environments. Engineering systems must be developed for permanent operation under conditions that exceed all historical experience. Settlement patterns concentrate in the twilight zones, where temperatures remain habitable, leading to population densities far exceeding anything in human history. These narrow habitable bands become the focus of all human activity and technological development. Transportation systems require complete redesign for operating between extreme climate zones. Travel between the hot and cold hemispheres becomes an extreme engineering challenge, requiring specialized vehicles and life support systems. Communication systems must bridge climate zones where equipment faces conditions ranging from extreme heat to extreme cold. Electronic systems require protection from both thermal extremes while maintaining reliable operation across the planet. Energy systems adapt to the availability of continuous solar energy in the sunny hemisphere, while relying entirely on stored or alternative energy sources in the dark hemisphere. Power transmission across climate zones becomes crucial for global civilization. Resource distribution becomes critically important, as different climate zones produce different materials and resources. The hot hemisphere may excel at solar energy production and certain industrial processes, while the cold hemisphere provides different advantages. Scientific research opportunities emerge as Earth becomes a natural laboratory for studying extreme climate conditions. Researchers can observe planetary-scale climate processes that normally require studying other planets or conducting computer simulations. As years pass, the divided Earth establishes new equilibrium patterns that demonstrate the planet's ability to adapt to radically different energy distribution patterns. Life persists in the habitable zones, while technological adaptation enables human civilization to continue under conditions unlike any in Earth's previous history. The divided Earth reveals the fundamental role that rotation plays in creating the moderate variable climate that has supported life throughout Earth's history. Without rotation to distribute solar energy evenly, the planet becomes a study in extremes that challenges every assumption about planetary habitability, while demonstrating the resilience of life and human civilization in adapting to radically altered conditions. Deep beneath our feet, in the molten realms where rock flows like honey and pressures exceed anything on Earth's surface, the planet's interior begins responding to the sudden cessation of rotation with adjustments that send seismic echoes through every layer of Earth's structure. These are not the familiar earthquakes of tectonic plate movements, but rather the deep groans and sighs of a planet settling into a new physical equilibrium as 4 billion years of rotational stresses slowly release their accumulated energy. The Earth's interior, hidden from direct observation, but revealed through seismic waves and magnetic field measurements, consists of layers that have evolved their current characteristics under the constant influence of planetary rotation. The liquid outer core, the plastic mantle, and the solid crust all bear the imprint of rotational forces that have shaped their behavior throughout geological time. When rotation suddenly stops, these deep layers begin adjusting to new stress patterns that propagate through the planet like ripples in a pond. The seismic waves generated by this adjustment process carry information about changes occurring thousands of kilometers below the surface, providing scientists with unprecedented opportunities to observe planetary-scale processes in real time. The liquid outer core, responsible for generating Earth's magnetic field through its rotational motion, continues spinning even after the solid Earth stops rotating. This differential rotation creates new patterns of convection and magnetic field generation that affect the planet's magnetic environment for centuries to come. The outer core, composed primarily of liquid iron and nickel, at temperatures exceeding 5,000 degrees Celsius, maintains its rotational momentum due to its fluid nature and enormous thermal inertia. This creates a unique situation where the liquid core spins within a stationary solid planet, generating mechanical stresses at the core mantle boundary, unlike anything in Earth's previous history. These differential stresses manifest as new types of seismic waves that propagate upward through the mantle and crust. Seismographs worldwide begin recording continuous low-frequency vibrations that represent the acoustic signature of a planet adjusting to fundamentally altered internal dynamics. Volcanic systems encounter modified conditions as magma chambers adjust to new pressure distributions and stress patterns. Some dormant volcanoes might become active as changing stress fields affect the pathways that control magma movement, while other active systems might become quiescent as their driving mechanisms change. The Ring of Fire, that belt of volcanic activity surrounding the Pacific Ocean, experiences changes in volcanic activity as stress patterns shift throughout the upper mantle. Volcanic systems that have been dormant for centuries might reactivate as new pathways for magma movement develop, while historically active volcanoes might cease erupting as their magma sources become redirected. Magma chambers, those underground reservoirs of molten rock that feed volcanic eruptions, face pressure changes as the stress fields that confine them adjust to the new rotational state. Some chambers experience increased pressure that could trigger eruptions, while others face pressure relief that might cause existing volcanic activity to subside. The deep ocean floors, bearing the weight of kilometers of seawater, begin adjusting to new loading patterns as ocean water redistributes from equatorial regions toward polar areas. These adjustments generate seismic activity that affects underwater ecosystems and alters seafloor topography. Oceanic trenches, those deepest parts of the ocean floor where tectonic plates dive beneath one another, experience altered stress patterns as the forces driving plate tectonics adjust to the absence of rotational influences. The subduction processes that have shaped ocean floor topography for billions of years face modification as rotational forces no longer contribute to plate motion. Mid-ocean ridges, where new oceanic crust forms through seafloor spreading, encounter changed conditions as the forces that drive plate separation adjust to new stress patterns. The volcanic activity that creates new ocean floor might increase or decrease depending on how stress redistribution affects magma production and movement. Continental crustal blocks, locked in their current positions by millions of years of rotational forces, experience new stress patterns that could affect the stability of mountain ranges and the locations of future tectonic activity. The continental drift that has shaped Earth's surface geography throughout geological time faces potential changes as the forces driving plate motion adjust to new conditions. The Himalayas, Andes, Rocky Mountains, and other major mountain ranges experience stress redistribution as the tectonic forces that created and maintain their elevation adjust to the absence of rotational contributions to plate motion. Some mountain ranges might experience increased seismic activity as stress patterns shift, while others could become more stable. Fault systems worldwide face altered stress patterns as the regional and global forces that load these geological fractures change in response to rotational cessation. The San Andreas Fault, the Alpine Fault, and other major fault systems might experience changes in their earthquake potential as stress accumulation patterns shift. Mining operations face new challenges as the stress patterns in underground rock formations change, affecting the stability of mine shafts and underground excavations. Deep mining operations encounter conditions that were not anticipated when the mines were originally designed and excavated. Coal mines, metal mines, and quarrying operations must reassess the structural stability of their underground workings as rock stress patterns shift throughout the crust. Mine safety protocols require updating to account for the gradual changes in geological stress that could affect tunnel and shaft stability. Geothermal energy systems experience changes as heat flow patterns in the Earth's crust adjust to new stress conditions. The geothermal gradients that make geothermal power generation possible might change as convection patterns in the Earth's interior adjust to the absence of rotational influences. Geothermal fields in Iceland, Yellowstone, Italy, and other geologically active regions face potential changes in their heat output and hot water availability as deep crustal heat flow patterns respond to altered stress conditions. Geothermal power plants might need to adjust their operations to account for changed thermal conditions. Underground water systems face modifications as the stress patterns that control groundwater flow through rock formations adjust to new geological conditions. Aquifers, those underground water storage systems that supply wells and springs, might experience changed flow patterns as rock permeability responds to altered stress fields. The global network of seismographic stations begins recording new types of earthquake activity characterized by different frequency patterns and energy distributions. These seismic events represent the planet's crust adjusting to new stress patterns rather than the sudden release of accumulated tectonic stress that characterizes traditional earthquakes. Traditional earthquake prediction models, based on the accumulation and release of tectonic stress, require revision to account for the continuous adjustment processes that replace the episodic stress release patterns of a rotating planet. Seismologists must develop new approaches to understanding earthquake activity that occurs as part of ongoing crustal adjustment rather than sudden stress release. The study of earthquake mechanics faces fundamental challenges as researchers observe seismic activity that follows different patterns from historical earthquake behavior. The mathematical models that describe earthquake occurrence require modification to account for the changed stress loading patterns in the Earth's crust. Gravitational anomalies begin developing as mass redistributes within the Earth's interior in response to the altered stress patterns. These anomalies affect satellite orbits, GPS accuracy, and precision surveying operations as the gravitational field that serves as a reference for these activities gradually changes. Gravity measurements conducted by research institutions worldwide begin recording systematic changes that reflect the ongoing redistribution of mass within the Earth's interior. These measurements provide unique insights into processes occurring deep within the planet that are normally impossible to observe directly. The Earth's moment of inertia, a measure of how mass is distributed within the planet, begins changing as internal mass redistribution responds to the absence of rotational forces. This change affects the planet's response to external gravitational influences and could subtly alter the dynamics of the Earth-Moon system. Deep drilling operations encounter modified conditions as rock properties change in response to altered stress patterns. Scientific drilling projects designed to study the deep crust and upper mantle face changing conditions as the rock layers they investigate adjust to new stress states. Oil and gas extraction operations experience changes in reservoir pressures and fluid flow patterns as the stress fields that control hydrocarbon migration adjust to new geological conditions. Petroleum engineering models require updating to account for the gradual changes in reservoir behavior. Underground nuclear waste storage facilities face potential challenges as the geological stability that these sites depend on for long-term safety could be affected by gradual changes in crustal stress patterns. Nuclear waste containment strategies require re-evaluation in light of the changing geological environment. The study of plate tectonics undergoes fundamental revision as researchers observe how tectonic processes adapt to the absence of rotational contributions to plate motion. The theory of plate tectonics, developed to explain geological processes on a rotating planet, requires modification for application to a non-rotating world. Continental drift patterns that have operated for hundreds of millions of years face potential changes as the forces driving plate motion adjust to new conditions. The supercontinent cycle, which describes the formation and breakup of continental landmasses over geological time, might follow different patterns in the absence of rotational influences. Paleoseismology, the study of ancient earthquakes through geological evidence, gains new importance as researchers seek to understand how earthquake patterns might change in response to altered crustal stress patterns. Historical earthquake records become crucial for understanding the transition from rotational to non-rotational geological activity. Geological hazard assessment requires comprehensive revision as the earthquake, volcanic, and landslide risks that communities face potentially change in response to altered geological conditions. Emergency planning and building codes must account for the possibility of changed geological hazard patterns. Research into the Earth's internal structure benefits from the unique seismic signals generated by the planet's adjustment to non-rotational conditions. These signals provide new information about the deep interior that supplements traditional earthquake-based studies of planetary structure. The field of geodynamics, which studies the forces and processes that shape the Earth, experiences a renaissance as researchers document in real time how a planet adjusts to fundamentally altered rotational conditions. This research provides insights into planetary evolution that would otherwise be impossible to obtain. Educational geology programs incorporate the real-time observation of planetary adjustment processes into their curricula, providing students with unprecedented opportunities to observe geological processes that normally occur over millions of years compressed into observable time periods. International cooperation in geological monitoring becomes crucial as the changes affecting the Earth's interior are global in scope and require coordinated observation and study. Geological survey organizations worldwide collaborate to document and understand the ongoing changes in Earth's internal dynamics. As months and years pass, the Earth's interior gradually adjusts to its new non-rotational state, establishing new patterns of internal stress and heat flow. The seismic signals that initially characterize the adjustment process gradually diminish as the planet reaches new equilibrium conditions. The deep Earth, in its ancient wisdom, demonstrates its capacity to adapt to fundamentally altered conditions while maintaining the basic processes that have sustained geological activity throughout the planet's history. The echoes from the deep provide a continuous soundtrack to the planet's adjustment, carrying messages from the Earth's interior about how a world built for rotation learns to function in stillness. In this transformed geological environment, the Earth's interior writes a new chapter in the planet's geological history, creating conditions that provide unique insights into planetary processes while establishing new patterns of internal activity that will shape the planet's geological future for millions of years to come. What emerges from the ashes of a world that stopped spinning? How does a planet that has lost its fundamental rhythm find new ways to sustain the life that has flourished for billions of years under the steady beat of rotation? The answers lie not in the immediate chaos of atmospheric winds and seismic adjustments, but in the slower, deeper processes of adaptation and equilibrium that begin to assert themselves as Earth settles into its new reality as a tidally locked world facing the sun with one hemisphere while hiding the other in permanent darkness. The new Earth that emerges from this transformation bears little resemblance to the planet that supported human civilization and familiar ecosystems. Yet within this alien world, the same physical laws that created the initial destruction begin establishing new patterns of stability that offer possibilities for life to continue, albeit in forms and locations that would be unrecognizable to inhabitants of the rotating world. Climate patterns gradually stabilize around the simple geometry of a planet with permanent day and night hemispheres. The continuous storms along the day-night boundary eventually organize into more predictable patterns as atmospheric circulation adjusts to steady-state conditions rather than the chaotic initial responses to rotational cessation. The twilight zone, that narrow band around the planet where the sun hangs forever at the horizon, becomes Earth's primary habitable region. Here temperatures remain moderate as the oblique sunlight provides enough energy for warmth without the extreme heating of the fully illuminated hemisphere, while avoiding the frozen conditions of the dark side. Water distribution reaches a new equilibrium as the continuous evaporation from the sun-facing hemisphere and precipitation in the dark hemisphere creates stable circulation patterns. Rivers form along the day-night boundary, fed by melting ice and condensation from the atmosphere, creating narrow habitable corridors where temperatures remain moderate and water remains available. These twilight rivers become the arteries of the new world, carrying water from the ice-covered dark hemisphere toward the parched sunny hemisphere, while providing the moisture necessary to support life in the narrow habitable zones. The river systems that develop follow entirely new patterns determined by thermal gradients rather than traditional watershed topography. Biological adaptation begins as surviving organisms encounter selective pressures, unlike anything in evolutionary history. Species that can tolerate extreme temperatures, utilize alternative energy sources, or exploit the unique conditions along climate boundaries gain advantages that allow them to expand into ecological niches that never existed on the rotating Earth. Plant communities develop new strategies for surviving in permanently lit or permanently dark conditions. Some species evolve mechanisms for continuous photosynthesis without dark periods, maximizing energy capture from the constant sunlight in the twilight zones. Others adapt to life in the perpetual darkness by developing alternative energy sources or entering extended dormancy states. Trees and shrubs that survive in the twilight zones develop unique growth patterns adapted to the constant angle of sunlight. These plants grow in distinctive shapes that maximize their exposure to the oblique solar radiation while minimizing water loss through transpiration in the dry twilight air. Animal populations that survive the initial disruption begin developing new migration patterns and behavioral adaptations suited to the stable climate zones. Migration routes develop along the day-night boundary where temperatures remain tolerable and water sources persist throughout the year. Birds that survive the magnetic navigation disruption develop new navigation methods based on the constant position of the sun and the reliable thermal gradients that characterize the twilight zones. These new navigation systems, while different from their evolutionary heritage, provide sufficient guidance for movement within the habitable regions. Mammals adapt their activity patterns to the constant light conditions in the twilight zones, developing new circadian rhythms based on temperature variations rather than light-dark cycles. Some species become active during the slightly cooler periods, when thermal radiation to space is most effective, while others remain active during warmer periods when solar heating peaks. Human societies, reduced to small populations in scattered refugia, begin developing new cultural adaptations for life in a world without day-night cycles. Social organization, work patterns, and technological development all require adaptation to environmental conditions that have no precedent in human history. Survivor communities concentrate in the twilight zones, where temperatures remain within human tolerance ranges and water remains available. These settlements develop new architectural styles adapted to the constant oblique sunlight and the need for thermal regulation in a world of stable but extreme temperature gradients. Housing designs evolve to maximize thermal comfort in the twilight zones, with structures oriented to take advantage of the constant sun angle while providing insulation against heat loss to the dark hemisphere. Building materials change to emphasize thermal mass and insulation properties rather than the structural considerations that dominated architecture in the rotating world. Technological systems require fundamental redesign for operation in the new climate regime. Solar power becomes continuously available in the day hemisphere and twilight zones, but completely unavailable in the dark hemisphere, requiring new approaches to energy generation and distribution that can operate under these extreme conditions. Energy distribution systems develop to transport power from the solar-rich regions to areas that depend on stored or alternative energy sources. Long-distance power transmission becomes crucial for maintaining technological civilization across the different climate zones, requiring advances in electrical transmission efficiency and storage technology. The oceans eventually stabilize into a new circulation pattern as the thermal gradients between hot and cold hemispheres drive currents that replace the rotational circulation systems. Marine ecosystems slowly adapt to these new current patterns and the thermal stratification that develops in the altered ocean basins. Ocean currents, powered by thermal differences rather than rotational forces, create new patterns of nutrient distribution and marine productivity. These thermal-driven currents operate continuously rather than seasonally, providing stable but different conditions for marine life adaptation. Marine life adapts to the new ocean conditions, with species migrating toward regions where temperature and nutrient conditions remain suitable for their survival. Cold water species concentrate in regions where the thermal-driven currents bring cooler water to the surface, while warm water species adapt to the heated regions or migrate toward more moderate thermal zones. Atmospheric chemistry reaches new equilibrium states as the continuous photochemical reactions in the day hemisphere balance against the preservation of compounds in the frozen dark hemisphere. The global carbon cycle reorganizes around these new chemical patterns, with carbon dioxide cycling between the hot and cold hemispheres through atmospheric circulation. Oxygen production continues through photosynthesis in the twilight zones, and any remaining plant life in the day hemisphere, while oxygen consumption proceeds at different rates in the hot and cold hemispheres. The atmospheric oxygen balance adjusts to these new production and consumption patterns over decades. Scientific understanding advances as researchers studying the transformed Earth develop new insights into planetary processes, atmospheric dynamics, and biological adaptation. The natural experiment created by rotational cessation, provides unprecedented opportunities to observe how planetary systems respond to fundamental changes. Research stations established in the habitable twilight zones become centers for studying the new planetary conditions and developing technologies for survival in the transformed environment. These facilities contribute to understanding how life and human civilization can adapt to extreme planetary conditions. Climate science evolves to understand the behavior of a tidally locked planet, providing insights that prove valuable for studying exoplanets in similar configurations around other stars. Earth becomes a living laboratory for studying planetary habitability under conditions that exist throughout the galaxy. Recovery efforts focus on establishing sustainable communities in the habitable zones while developing technologies for survival in the extreme conditions. Humanity faces the challenge of maintaining civilization and knowledge while adapting to environmental conditions that eliminate many assumptions about planetary habitability. Agriculture develops new techniques adapted to the stable but extreme climate zones. Greenhouse agriculture becomes essential in regions where outdoor growing is impossible, while outdoor farming in the twilight zones requires adaptation to constant oblique sunlight and thermal gradients. Crop breeding programs focus on developing varieties adapted to continuous light conditions, extreme temperature ranges, or the specific thermal and moisture conditions of the twilight zones. Traditional agricultural genetics require significant modification for the new environmental conditions. Water management becomes crucial as communities develop systems for collecting, storing, and distributing water in a world where precipitation patterns follow entirely new rules. Ice harvesting from the dark hemisphere and atmospheric water collection in the twilight zones become essential technologies. Transportation systems adapt to the need for travel between extreme climate zones. Vehicles must be designed to operate across temperature ranges from space-like cold to desert-like heat, requiring advances in thermal management and life support systems. Communication networks develop to maintain contact between widely separated survivor communities. Radio and satellite communications must be adapted for operation across extreme temperature zones while maintaining reliable connections between isolated settlements. International cooperation becomes essential as survivor communities share resources and knowledge necessary for adaptation to the new planetary conditions. Trade relationships develop based on the different resources and capabilities available in different climate zones. Manufacturing systems adapt to utilize the different advantages offered by each climate zone. Solar energy abundance in the day hemisphere, thermal differentials in the twilight zones, and potential superconducting conditions in the dark hemisphere. Each offer unique industrial possibilities. Educational systems develop new curricula focused on survival skills and technologies appropriate for the transformed planet. Knowledge preservation becomes crucial as communities work to maintain scientific and cultural heritage while adapting to fundamentally different environmental conditions. Cultural evolution accelerates as human societies adapt to environmental conditions that eliminate many traditional practices, while requiring new forms of social organization. Art, literature, and music evolve to reflect the experiences of life in a world without day-night cycles. Religious and philosophical systems adapt to help people understand their place in a fundamentally transformed world. The concepts of time, season, and natural cycles require reinterpretation in a world where these traditional markers no longer exist. As decades and centuries pass, the new Earth develops its own characteristic patterns of weather, ocean circulation, and ecosystem organization. Life demonstrates its remarkable ability to adapt and persist even under conditions that eliminate the environmental stability that supported previous evolutionary development. Species that successfully adapt to the new conditions begin diversifying to fill the ecological niches available in the transformed world. Evolution accelerates in some lineages as they adapt to the extreme selective pressures, while other evolutionary lines persist in relict populations confined to the most hospitable microenvironments. Ecosystem development in the twilight zones creates new types of biological communities based on the unique conditions of constant oblique sunlight and thermal gradients. These ecosystems, while different from any that existed on the rotating Earth, demonstrate the flexibility of biological systems in adapting to novel environmental conditions. Human population growth eventually resumes in the habitable zones as communities establish sustainable relationships with their transformed environment. Population genetics evolves as isolated communities adapt to local environmental conditions over generations. Technology continues advancing as human societies develop increasingly sophisticated methods for thriving in the transformed world. Space technology becomes particularly important as off-world colonies offer alternatives to the extreme conditions on the tidally locked Earth. The dawn of this new world reveals not the end of Earth's story, but rather a new chapter in planetary evolution, where life learns to thrive under conditions that test every assumption about the relationship between planetary motion and biological possibility, creating a world where adaptation becomes the key to survival in an environment unlike any that has existed throughout the history of our formerly spinning world. In this transformed reality, Earth demonstrates the fundamental resilience of planetary systems and the remarkable adaptability of life itself. The new world's dawn illuminates a planet that, while alien to its former self, continues to support the complex processes of life, evolution, and human civilization under conditions that reveal new possibilities for existence in a universe where tidally locked worlds may be far more common than the spinning planet that once supported the rise of human civilization.